Welcome to the second technical session of national level webinar jointly organized by Department of Chemistry and Internal Quality Assurance Cell of Hooghly Women's College. I am Dr. Anup Biswas, Assistant Professor of Chemistry of Hooghly Women's College. On behalf of organizing committee, I welcome all the participants to the second day of the webinar. This technical session will contain two plenary lectures. Let me introduce the first speaker of this technical session. Today's first speaker is Professor Suman Desarkar from Indian Institute of Science, Education and Research, Kolkata. Professor Desarkar completed his BSc with honors in chemistry from Vivekananda Thakurpukur College, and then he moved to Indian Institute of Technology, Kanpur for his MSc. After completing the MSc, he received NRW Graduate School of Fellowship from University of Münster, Germany, where he joined Professor Armido Studer's group as a research fellow. He completed his PhD in the year 2010, and then he moved to University of Basel for his first postdoctoral research, and he joined Professor Karl Gardemann's group. And after his first postdoctoral research, he moved to University of Göttingen to work with Professor Lutz Ackermann after receiving very prestigious Humboldt postdoctoral fellowship. He came back to India and joined as an assistant professor at IISER, Kolkata in the Department of Chemical Sciences in the year 2015, where he is now working as an associate professor. Professor Desarkar's research mainly focuses on electrochemistry, metal and cooperative catalysis, and photoredox catalysis. Today, he will speak on heterocycle synthesis by redox state manipulation. Professor Desarkar, I would like to request you to start the session. Thank you. The platform is now yours.
Okay, very good morning to everyone. Anup for this very kind introduction. And first of all, we appreciate taken by Hooghly Women's College. Big thanks, Professor Goswami, of course, Anup, and all other person who is associated with this initiative. So, as I said, I really appreciate this. Really a good platform to knowledge to the audience, which have been possible in knowledge and taking advantage of this pandemic season, with this new normal, and taking advantage of we are reaching. So I really appreciate that. And of course, I'm very happy to share some of the that we are doing here in IISER, Kolkata. So I would start as you know that I will just show PowerPoint presentation. So let's start. Just a moment. Presentation mode. Is my
Yes, it is now present here. Yeah.
Is it visible now?
Yes, yes. Let's continue.
Perfect. So this is the main gate of IISER, Kolkata. To enter, go there, and then this is the gate. And once situation is normal, I will invite you all to visit. There is one day, Wednesday, where our gate to everyone, whoever interested to see, know about science, what we are doing. So please visit us and visit the labs, and especially the students. So they will definitely get motivation from this. All right. Already Anup said that I will today the heterocycle synthesis by redox state manipulation. We're going to the details of presentation, let me briefly tell you about our group activities. So we called our group Redox Group, okay? And this one is our group logo. So this one is our group logo, as you see. So it's OX, okay? So this red stands for reduction, and the OX stands for oxidation. So just doing these two transformations, just by doing reduction and oxidation, we are developing new methodologies for the synthesis of important organic molecules, okay? And there are mainly 4 different ways, different techniques we are using for these redox manipulations. So one is redox using light, so that is called photoredox, okay? Second is using different catalysis, mostly transition metal catalysis, and also there are some using transition metal catalysis, and sometimes you don't really need any catalyst, just using base. I will show one transformation just using base there and transferring the hydrogen, okay? So as you know, by definition, taking out hydrogen from a substrate is doing hydrogen is reduction. So with that, taking the advantage, we are developing these new organic molecules or important organic molecules. The third one is using redox chemistry using electrochemistry, just by pushing electricity, okay? So this is comparatively new and getting very much interest in the community. It's a hot topic now, just by passing electricity doing redox chemistry. I will this in a minute. And last but not the least, the most classical way of doing redox chemistry, just by using stoichiometric amount of redox reagent like DDQ or many other CAN, ammonium nitrate, or many other these hypervalent way of doing redox chemistry. We are also involved in this project. But today, as you know, the time is short, so I will try to speak about 50 minutes or 55 minutes. So I will not show the other two, the photoredox, I will not get time to show, and also this classical approach. I will mainly focus on this hydrogen transfer chemistry. Briefly, I will show you a little glimpse of this electroorganic chemistry. All right, so let's begin. So what is this hydrogen transfer chemistry or borrowing hydrogen chemistry? Let me first tell you a very general concept. So in my presentation, what I will do, I mean, I don't like to show many reactions. Try to go very slow and give you, try to give you the basic concept about the reactions. So in case you have, of course, I will try to explain things, but there will be some technical things which will be probably a little bit difficult to understand. Please write in the chat box. I will try to explain those things as well. All right, so what is this borrowing hydrogen? I'm sure for many of you, this is a new terminology, borrowing hydrogen concept. So what is that and why we need that? The thing is, so when we plan a organic transformation, okay, so suppose this is the starting point and we want to make it. And in many times it happens a direct transformation from this starting material to the target molecule is not possible, because this the starting molecule is not reactive enough. Okay? We need to activate that molecule. So there is one way to activate this non-reactive substrate is to do redox manipulation. We can use a catalyst which will activate this non-reactive substrate by just taking out hydrogen. Okay, once you're taking out the hydrogen, it will form a very reactive substrate. So later on, I will give you a more specific example so that you can understand better. Okay, so once you form this reactive substrate, now you can do reaction and you form this reactive substrate. And at the end, so the catalyst which took out some hydrogen from the substrate, it will give back this hydrogen to this reactive substrate and it form the targeted molecule. Okay, so this is the concept. And now why this is called borrowing hydrogen? So as you know, what borrowing is something you take something from someone else, and use it for some time, and at the end you return it. That is borrowing. You see, the catalyst is exactly doing that. So catalyst is borrowing some hydrogen from the substrate, and at the end it is giving it back and is regenerating the catalyst in going back to the initial. So that's why it's called borrowing hydrogen concept. So let us explain this with more specific example. So suppose you have an alcohol, okay? So alcohol, and you want to substitute this OH group with some nucleophile. Let's take an amine. So now if you mix one alcohol with an amine, react, right? So because amine is a good nucleophile, but this OH group is not a very good leaving group, right? So that's why the amine will not really react with through a nucleophilic attack, because this OH minus is not a good leaving group. You really need to convert this OH into a very good leaving group like tosylate or mesylate, or convert it to a iodide or whatever. Then the amine will react through nucleophilic substitution, right? Normally it will not react. But once you convert it to a good leaving group, as I said, tosylate or mesylate or halogen, it's additional step, and additional step and additional reagent as it additional expenditure. Can we bypass those by doing redox manipulation? Yes, we can. So just by using an appropriate catalyst, what we can do, we can just take out these hydrogens from alcohol, and you can form a carbonyl group. Now, once you form the carbonyl, aldehyde or ketone, which is pretty reactive with amine, as you know, if you say amine, it will immediately form the Schiff's base or imine product with the release of water. And once this imine is formed, as we mentioned, the metal catalyst took out hydrogen from the substrate, and this is waiting with those hydrogen, and it will now give back that hydrogen to this imine and form this product. So now you see, we started from it here, of course not directly, but via this route. Okay, so this is the borrowing without using any oxidant, any reductant, or without converting it to a very good leaving group, just by doing redox manipulation. First converted to aldehyde, then imine, and then reduction of the imine got our targeted. Okay, so this is the concept. So people have already worked on this. It's a beautiful review by Rodriguez and co-workers on ChemCom 2016. Whoever interested in this topic, I really highly recommend them to read this review. Okay. So this is the borrowing hydrogen thing. So there is another concept which is almost similar but little bit different. Okay. Is suppose if starting from the alcohol, you want to stop it the imine state itself, or you don't want the last hydrogenation step. Okay, so in that case, you have to plan or design the catalyst so that the metal catalyst will take out the hydrogen from your substrate, from the aldehyde, and from the imine. But this metal catalyst which took out the hydrogen at the initial stage will not give back the hydrogen to the imine. Rather, it will just release the hydrogen as H2. Okay. So that's why, so this is not really borrowing hydrogen, because metal catalyst is not giving at the end, rather it is releasing as hydrogen, H2, dihydrogen. That's why this is called a dehydrogenative approach. Okay, so previous one was a borrowing hydrogen approach, and this is dehydrogenative approach. All right, so these are the two concepts. It's mentioned nicely in this review. But so when we started in 2017, so then we really wanted to contribute and use this concept and develop some new methodology and some important molecules. So at the beginning, we found that this quinoline moiety is a very important heterocycle. So there are a bunch of biologically important compounds which are known quinoline moiety. I just listed few of those, like this anti-tumor and antibacterial, and of course some very antiviral. These days antiviral things are important, so there are many antiviral also activity are there. So now if you see the classical approach for the synthesis of quinolines, what are those? In your inner book or this heterocycle Julian Smith, you will see there are so many classical syntheses are there. So one of those are base synthesis, COP synthesis, and you see there the disconnection is like this. You see in all this, most of the cases the disconnection is here and here. So basically they start with aniline derivative and this 1,3-dicarbonyl, okay, in both cases. Or you can skip this just by doing an alpha beta unsaturated ketone or so. But the problem here is in most of the classical synthesis, you really strong acid or very strong oxidant, and the substrate scope sometimes is very, very low. okay, because many of the functional groups cannot harsh condition. In our research program, we really wanted to do something very mild, okay, and our section you see is a little bit different. So we thought we can cut it here and cut it here, and we show that we can synthesize our quinoline from this alpha amino ketones or acetophenone derivatives or benzaldehyde, okay. But we will not start from here. As we say, we will take the advantage of borrowing hydrogen. We will rather start from here, that alpha amino benzyl alcohol derivatives, which are very cheap and easily available. And the other partner should be alcohols. As you know, alcohol is very cheap. So just mix cheap reagents or reactants just by using a appropriate transition metal. Can we prepare this valuable quinoline? So that was our research program at the beginning in 2017. Yes, and we worked on this, and of course we succeeded. So what we use this nickel-based catalyst, nickel-based, which is can easily synthesize following this procedure. We synthesize that and use very tiny amount of this catalyst, just mixing these two alpha amino benzyl alcohol, and along with another alcohol, partner alcohol, or a ketone, and these two just fragments just combine with each other form this quinoline derivative. So this is the exact reaction condition. This benzyl alcohol, different ketones, nickel, this nickel catalyst, only 2 mole%. Probably I will better to go for the laser. It's the pen. Just a moment. Here. So this nickel catalyst, 2 mole%, and 120 degree, nothing else, no oxidant, no reductant, only some amount of base we need. I will show why we need the base later on when I will show the mechanism. These two fragments combined with each other. So the blue fragment comes from here, the black fragment comes from here, the red bonds, which are the new, and it form this quinoline derivatives. We just varied the substrate scope. So whenever we generate or develop a new methodology in organic chemistry, we need to substrate scope, and we did a lot. I'm just showing a few of those. So I don't remember exactly, probably we did 20 of those. I'm just showing you five. So here what we did, we just varied this part, okay, and keeping this as acetophenone. As you can see, the substrate scope is very general. And later on, what we did, instead of taking a ketone, we took alcohol, and in both cases alcohol, we got this product. Later on I will show you the mechanism. Just don't worry about the mechanism right now. Okay, here we go. This is the mechanism. So I'm telling you what to the audience. So in my presentation, the take-home message is the concept and the mechanism. So in the mechanism slide, you please pay attention. Okay, the substrate and there, but just by reading the paper or something, you will understand. But the mechanism, that is the most important thing. If you understand the mechanism properly, then only you will get the concept, and you can develop something new. Okay, so what's happening here in the mechanism? So we are starting here. So this is the starting benzyl alcohol. All right, benzyl alcohol compound, orthoamino compound. So what's happening? This is the nickel catalyst, and in presence of base, the base will deprotonate this OH. Okay, making O minus, and once it's formed, a O minus is a good ligand, and this is the nickel catalyst. It will coordinate with the nickel catalyst, the oxygen. So once we form this coordinated with oxygen, now you see one beta hydride is waiting there. So what will happen? So it will undergo a beta hydride elimination. And this will come to the metal, it form the nickel hydride, and it's a double bond here. So we release a carbonyl compound, alpha, this orthoamino benzaldehyde. Okay, the same can happen with the other partner alcohol. All right, so here also you can undergo this dehydrogenation here, hydride transfer, and form this ketone and form the nickel. All right, so once you see, now we started with alcohol, now what we have a ketone and another aldehyde, and we have base. As you know, once we mix ketone, aldehyde, and base, what will happen? It's simple reaction, aldol reaction. So definitely it will undergo an aldol reaction. So once we form this aldol reaction, this OH is here. So now this aldol can it can go undergo this water elimination and form a double bond here, alpha unsaturated ketone, right? And it can equilibrate because this can be reversible, and water can also add here and give back this. And once we have, and this ketone can cyclize and then follow up water elimination, will give you the targeted quinoline product. Okay. So there is another possibility. This is one possibility. So what can happen? Once you form this ketone can also condense with this amine. Instead of forming this aldol reaction first, it can condense with this amine and form this imine. Once it form this imine, now it can undergo intramolecular aldol reaction here and form this ultimately the product with following couple of steps. So we are not sure at that time. So whether this carbon-carbon bond formation first and then carbon-nitrogen bond formation, or other way around, first carbon-nitrogen bond formation and then carbon-carbon bond formation. Okay, so then what we did a control experiment. We prepared this compound. You see, this alpha beta unsaturated ketone with a amine ortho to this, using a separate method, not using our this exact method. Okay. So now you see this compound is basically an intermediate here. If the reaction going via first carbon-carbon bond formation, then only this is forming. Okay. So we took this compound and then we put this nickel catalyst, whatever the standard reaction condition, nickel, base, and everything, and we heat it up. That this is exactly forming the quinoline. Okay. And there is also another interesting observation here. When we did the reaction anhydrous condition, that means no water there, only using dry toluene, then the yield was very low, 15%. The reaction is also very slow. But once we add little bit of water, then it becomes much more, 55% yield. And of course, there is a reason for this, that what's happening, once you see here, this is a trans double bond, and the next step is the amine will attack here on this ketone, and it's a cyclization here, right? But once it's trans, then it's, you see it's far away from each other. It's amine can't really react with. But once we have water here, if you add water, what will happen? This water will undergo this oxo-Michael addition here with a OH here, and once it becomes a single bond after Michael addition, this becomes flexible, and this bond can rotate easily. And if it's rotate, then this ketone will come close to this amine, and then it can condense easily, and the quinoline product. That's why in presence of little bit of water, the reaction efficiency is much more. And but just by doing this control experiment, now we are sure that this reaction is going via this first carbon-carbon and then carbon-nitrogen, not via this. Okay, just by doing this control experiment. All right, I hope this makes clear to all of you. Next, after preparing this quinoline derivative, we focused on another important heterocycle. So that was benzimidazole. So previously it was 6,6, and now you see 6 and 5. Okay, with 2 nitrogens. So benzimidazole. So that is also very, very important molecular scaffold. As you see, this is antiviral, antimicrobial, anti-tumor, and many more. And here also, if you see the classical synthesis, in classical synthesis, all use these diamines, because you see you need a diamine. So people use a diamine, orthosubstituted diamines, and one acid derivative, whatever you can take, ester or acid chloride, and you really need to heat with a very harsh condition, strong temperature, and so on and so forth. Sometimes strong oxidant also. But one problem, there are a couple of problems. One is these acid derivatives are comparatively expensive. Okay, so if it would be nice if you can do it with alcohol, benzyl alcohol. Okay, so this another problem is these diamines. These diamines are not very stable. So already, I don't know, probably many of you handled aniline in your lab, right? So and after sometimes you will see the aniline bottom becomes black, and actual pure aniline that is transparent, colorless liquid. But after sometimes it becomes black or reddish thing, right? So I'm sure that this is because this is the aerial oxidation of aniline. Aniline is an electron-rich system, and with the aerial oxygen, it gets oxidized, benzoquinone, and many. Okay. Think about now this aniline, right? So with aniline means only one nitrogen. Now it's having 2. electron rich and it's really get in air. And this is really need a special precaution to store it. Okay, otherwise these are the problem here. So how can we solve that? We really need something stable, and it was our target, right? We thought the ortho-nitro aniline derivative. Okay, ortho-nitro. So you see the presence of this nitro group will deactivate this aromatic ring. So now it's much more stable. It will not get oxidized that easily. And as I said, these acid derivatives sometimes are costly, but the corresponding are cheaper. Okay, so can we use that? Yes. So now here the concept is we'll use this alcohol. So now, and using, as at the beginning, as I said, it's a hydrogen transfer or borrowing hydrogen concept. Can we use that concept and transfer these hydrogens from here with the list from this alcohol to this nitro? Okay, so if you transfer this hydrogen from alcohol to nitro, what will happen? Will from this alcohol will form an aldehyde. And if you try get this nitro groups gets the hydrogen, that means a reduction of nitro, it will form the amine. Okay, so in what we can form this diamine and this aldehyde, or right? So now it will immediately react with each other. So we are starting with a stable compound which is much more stable, but in situ in the reaction flux itself will form something which is reactive. So that is the concept. Okay, so we did that, and we really used a very cheap. This is cobalt ACAC 5 mole%. Here also no additional oxidant, no additional reductant. Okay, and just heating is mixed to in presence of base. With these two, we nicely got this Benzimidazole products. Okay? So here also we did a lot of substrate scope. I am showing you only very few. So in this part, we got this substrate. Then we varied both with this part and as well as this part, and you can see in all cases we got a good to excellent yields. All right. Again, the mechanism, as I said, always the most important is the mechanism. So what's happening here? This is the cobalt catalysis. So this is the starting point. The first step, again, from the previous nickel catalysis, we have a base, we have alcohol here, and the metal catalyst. It will deprotonate the base, and the metal, this alcohol will coordinate with the metal, and the beta hydride elimination will give you the aldehyde molecule, okay, and form the cobalt hydride. Now, once you form the cobalt hydride, the cobalt transfer or reduce this nitro group, metal hydride will reduce the nitro group to amine. So once we have the amine in situ, diamine and aldehyde, definitely it will condense. So there is a nucleophilic adduct here. First imine and then other nitrogen will attack, form this 5-membered ring. Once we form this, again another with using the same catalyst, same cobalt, with the oxidation here, form this new double bond to release the product, your Benzimidazole product, with the help of with the release of cobalt hydride. And now again this cobalt hydride with the reduce another molecule of another nitro functionality here 1A, and it form the diamine. So this cobalt. So this cycle will go on and go on. That's why only 5 mole% of catalyst is good enough to do this redox manipulation. That's why in my title I said it's a redox manipulation. Now you can understand. I hope you are understanding the why I'm saying redox manipulation. What we are doing, we are oxidizing this alcohol and reducing the and form amine and aldehyde, corresponding aldehyde. Okay, redox manipulation. Oxidation for one, reduction for other, without using any oxidant reductant, only using metal catalyst. Okay, so this is the concept. And of course we prove our mechanism just by doing a couple of control experiments. What we did, you see, we intentionally diamine, okay, and one alcohol, okay, and we treat under the whatever standard condition, metal, base, and everything. We did not get any product. Why not? Because when this is diamine and this is an alcohol, okay, so what will happen? So so there is, you see, whatever the metal catalyst after oxidation is forming the hydride, we need a nitro functionality to regenerate the catalyst. Okay, if the nitro is absent, this cobalt hydride will not regenerate the cobalt. Okay, and if you don't regenerate the cobalt, you will not get oxidize this alcohol to aldehyde, so reaction will not happen. So this is kind of complementary to each other. You you really need the alcohol, then only it will work. So the only taking alcohol and diamine without nitro, it will not work, did not work. Or other way around, also true. Now we took only amine and nitro, and instead of taking alcohol, we took aldehyde. Okay, here also reaction failed. Why not? Because if you don't here, from the cobalt catalyst, we will not be able to form cobalt hydride. Okay, will not be able to form cobalt hydride. And once we don't form the cobalt hydride, there is no one to reduce the nitro. And once we don't reduce the nitro, you will not form the diamine, and it will not form the product. So this is the concept. As I said, these are complementary. And if we take nitro and alcohol, then only this reaction will work, otherwise not. And also by doing this control experiment, we prove our concept and prove our proposed mechanism. All right. So this is the second project. So let's move on. So next I will tell you about something little bit different, is fluoroalkylation. Okay, so this is related to the synthesis of heterocycles, which is the major topic of my today's presentation. But this is kind of functionalization of heterocycles. So and this is one of the best project. It is it's close to my heart. That's why I am showing you this. And let me first tell you the importance why you would like to do that. Because these fluorinated compounds, these fluoroalkyl chains are very, very important. So it's really important. And if you see the natural products, so I think 5 or 6 natural products are existing which contains fluorine molecule. Okay. But if you see the pharmaceutically important molecules, so it's as you know probably that all natural products, so whatever functional molecule we are available in market or the medicine, all many of those are not made artificially in the laboratory by chemists, right? Those pharmaceutical molecules, huge number of having fluorine, almost more than 50% molecule are containing fluorine. Okay. So if you incorporate fluorine in a pharmaceutical compound, the metabolic stability of this fluorine, those compounds increase drastically. Okay, that's just suppose this molecule having a methyl group here, whatever the stability or activity, once you just replace methyl with CF3, the activity increases in most of the cases. Okay. So that's why this fluoroalkyl chains, or introducing fluoroalkyl chains, or adding fluoroalkyl chains in an organic model, very, very important. Okay. And people are really looked for different reagents and different methods to incorporate these fluoroalkyl chains in organic molecules. There are few reagents which are available to do so. So one of those is this Togni's reagent. Okay. This is called Togni. So Professor Togni, he developed this reagent, hypervalent reagent. And there is another reagent based on this hypervalent sulfur. These are the common reagent and popular reagent to introduce fluoroalkyl chain in an organic molecule. But the problem is, look at the price. This 100 gram of this Togni's reagent cost 6,246. It's really only tiny amount, 100 milligram. But which is really difficult to do a larger scale. So what are the other plans? What are the backup plans for this? What are the solutions? Okay. So can we use these fluorinated alcohols? See, this is, for example, trifluoride or this pentafluoropropanol as a fluoroalkyl chain source, which are, look at the price, which is much, much cheaper. Is this 100 gram of this cost 950 rupees compared to 100 milligram 6,246 rupees. It's a hell and heaven difference, right? But we thought to take this advantage here and use this instead of using this very expensive reagent. We thought to use these cheap ones and developed a new method to introduce fluoroalkyl chains. So this is our concept in one line. So we thought to use these fluoroalcohols and do this metal catalyzed dehydrogenation, as I showed at the beginning, and form this reactive carbonyl, and then using a nucleophile will introduce this fluoroalkyl or add this fluoroalkyl in the organic molecule. This is the concept, and later on I will show you in more details. Okay, so on paper it looks simple, but in reality it's really, really difficult. Why? In the first two, I told you about the dehydrogenation of benzyl alcohols and other alcohols, right? So there, those things are much easier. Okay, but once from those benzyl alcohol and simple alcohols, once we go to fluoroalkyl alcohols, the things really changes drastically. Here, is this because this dehydrogenation alcohols, okay, is very difficult. Once we, so the common mechanism for this dehydrogenation, as I mentioned already, so with the transition metal will sit here on this alcohol, and there is a beta hydride elimination, right? As I mentioned in the previous two examples. But this beta hydride elimination is very difficult for fluoroalcohols. Okay, this is because of this large destabilization of these fluoroalkyl groups. As you can see, for the beta hydride elimination, you really need to generate a delta positive, a partial positive charge on this carbon. And if it's a strong electron, longer chain of fluorine is there present already, it will destabilize this transition state. That's why for benzyl dehydrogenation is much easy, but for these fluoroalcohols, it's much more difficult. It's a high energy process. And there is very few reports on this. There is only one literature. This is Professor Krische from US. So they are really pioneer of this dehydrogenation and borrowing hydrogen concept. So they published in 2015. This is Anguante Chemie. This is high impact journal. So what they did, they used a ruthenium catalyst and did this dehydrogenation, and they add one nucleophile here. But as you can see here, so their method is the only method, and that's also having a lot of drawbacks or limitations. They could not do with trifluoroethanol. When they took trifluoroethanol, they got 0% yield. When they took this trifluoropropanol, they also got less than 5% yield. They could succeed with 60% yield when the CF3 is far away from this OH group. Okay, far away. Then only they succeeded. Okay, so they got some success, but it's a partial success. There are still a lot of limitation. And in our research program, we really wanted to develop one method which is very general. So we alcohols and all kind of fluoroalcohols, which when the fluorine is close to the alcohol, far away from the alcohol, all kind of alcohols, and which will dehydrogenate. And using a nickel catalyst, of course, ruthenium is much more expensive compared to nickel. So we wanted to with a cheaper catalyst as well, and we developed this method mechanism. Yeah, what's going on? First, let us first see the substrate scope here. So we took this alcohol and this nucleophile as the indole product, and a nickel-based catalyst, and we we use these all alcohols here, different alcohols, all kind of fluoroalcohols is working. Fluoroalkylation, so two indoles comes together and join here, and we introduce these fluoroalkyl groups in the organic molecule. That was our motivation and target, and we really succeeded that. Okay. Mechanism. Before going to the mechanism, I would like to show you a couple of control experiments. Right, I will go to the mechanism and I will explain you in more details how these two indoles are coming together and forming this indole product with fluoroalkyl group. Okay, so what we did, we synthesized. So initially we were taking what? Indoles only. Now we intentionally synthesize this molecule. Okay, with CF3OH using some other methods. Okay, using this, and then we mix these two and our standard reaction condition, whatever, we got 16% yield of the product. Okay, so although yield is low, but it's a control experiment, so we don't care much. So now, as you can see, if we use this indole and there is no other trifluoroethanol source, okay, CF3 must be coming. The CF3 must be coming from this. So this control experiment proves what? Proves that this CF3, this molecule is an intermediate of our reaction. So in the mechanism, in some stage this is forming, and then it's reacting with another molecule of indole and forming this bis indole product. All right. We did another control experiment. So in that case, so we proved that we checked whether in our reaction hydrogen is forming or not. Okay, whether hydrogen is forming or not. So what we did, we took the whatever standard reaction condition our nickel catalyst and everything, the indole and trifluoroethanol. Do it with the reaction flask, we attach one tube. Okay, with the reaction flask, we attach another tube, one tube, and put in that tube. Put this tube in another flask, so that in the whatever gas will form in this reaction, whatever gas will form, we transfer and go to the other reaction tube. Okay, so this is the engineering we have done. And the second tube, what we took, styrene and palladium charcoal. Okay, so palladium charcoal is a hydrogenation catalyst, and styrene, of course, as you know, it's with a double bond here. So whatever hydrogen is formed here, with absorbed on this palladium and then reduced, and we got this ethyl benzene. We can detect this by GC analysis, and we could see that 10% yield is there. Okay, so that means indeed the hydrogen is forming in our. So just by doing these two control experiment, we got this information that this is one of the intermediate in our reaction and forming in our reaction. All right. And then we, of course, also did some DFT calculation. So this part, this lower part, I will come in a minute. Okay, so better, it will be easier to explain afterwards. Better, I will go to the next slide and explain you the real mechanism. Of course, there is a lot of information is here. I want you not to look at this data, I mean, these numbers. Rather, you focus on the structures. I will explain the things. So what's happening here? So this is our nickel catalyst, all right? And this is the alcohol, and we have base. So once we, in presence of base and alcohol with the nickel catalyst, as I mentioned, the base will form and coordinate. This alcohol will coordinate with the metal catalyst. So once you form this metal catalyst, and then it will undergo this beta hydride elimination via this transition state. This is the DFT calculation. So in collaboration with Professor Lisa Roy, so she did these things. And she had showed different, check different energy, not to focus on this, just on the structure, as I said. So once via this beta hydride elimination, via this pathway, it's released this trifluoroacetaldehyde, okay? And this nickel hydride, which will again deprotonate this another alcohol and go back to the initial stage. So this is fine, but this is important. Thus, it is forming trifluoro, which is very, very reactive. Trifluoroacetal, normal acetaldehyde is already reactive, and trifluoroacetaldehyde you can't really purchase. It's always in normal case, it's always in hydrated form. Okay, trifluoroacetaldehyde in situ we are generating, that is very, very reactive. And once you form this, you have indole there, which is a good nucleophile. This is very reactive. It will react with this and form this intermediate. And from the previous case, right? So in the previous slide, I have showed you one control experiment when we started with this. Okay, but the product, right? So you see, this is, that means this is one of the intermediate in our reaction. So this is the first step. This is forming this intermediate. Once you form, so now this nitrogen will donate lone pair and then kick out water from here and from this intermediate, which is another reactive intermediate. And again, another molecule of indole will come here and attack here. Okay, the nucleophilic attack again here. Once we attack here, and so two more indole molecules so join together, and you introduce this groups. It's the same mechanism for the other alcohols also. So as I said, so Lisa calculated the performed different DFT calculations, and then I just want to briefly mention. I will go back to the previous slide. So she found that this indole is having a dual role, and then this is some pi stat, and this is which is responsible to lowering the energy of the transition state. That's why the beta hydride elimination is feasible in our case. That's why our method is special. So no one could, as I mentioned, no one could ever succeeded to hydrogenate trifluoroethanol this efficiently. So we are the first one to do that, and this the reason is this indole is doing some pi stacking, and there are some secondary interaction. But for the beginners, it's not important. I hope you understood the basic mechanism. All right. So this is good. So this is the mechanism. It's from the base indole. So far, whatever I told you. All right. So these are all planned. As you know, at the beginning wanted to prepare quinoline. We prepared quinoline. Then we prepared to prepare benzimidazole. We prepared benzimidazole, and the third project, as I showed you, we wanted to introduce fluoroalkyl group. We introduced fluoroalkyl group in indole molecule using this catalytic dehydrogenation or borrowing hydrogen concept. But in research, sometimes the things will not go in a plan. So whatever you planned and you do the reaction in the laboratory, and you found something else. Okay, so and there was something else which is unplanned things, which this is more interesting or more important than that. Okay. And those kind of things are called serendipitous discovery. And in science, there are so many important discoveries which are just happened by accident, and those are serendipitous discovery. Probably a story of penicillin discovery, and there is many other, right? So this serendipitous discovery, and exactly same happened with us also. So we planned something and we got something else, okay, which is more important and interesting. So let us have a look on this in this project. So we wanted to do one classical this as a transfer or substitute this OH group with amine. Okay, just a standard amination reaction using borrowing hydrogen concept, and we wanted to develop a new nickel-based catalyst. Okay, so the student the Devabroto, he did this reaction, and but then he did little bit modification. So what he did, he took only, instead of normal aniline, he took ortho-iodo-aniline. This is the modification. Now you see previous case, so what we got? Only this carbon-nitrogen bond formation here. Once we just ortho-iodo-aniline, you see we got another new carbon-carbon bond formation, okay? And there is no iodine left in this molecule, okay? So we are really surprised and we are really excited. What's happening here? So in one step, we are forming one carbon-carbon bond, carbon-nitrogen bond, and another carbon-carbon, and we make heterocycle, which is also very, very important. Okay. So then we got excited and we are interested on this project. At the beginning, we are thinking that we are having some CH activation here, as Professor Maji yesterday showed. So I'm sure some of you also attended his lecture. At the beginning, we thought this is a CH activation reaction. We found it's not. It is something else is going on here. So what's happening here? So this amine, it's actually forming this imine. I will come later on with a more details mechanism, just to want to show you the concept here. And then it's forming an aryl radical here. Okay. And once you form this aryl radical, coupling with this other aryl ring and forming this new bond. Okay. And we also found that we don't really need any catalyst. No metal catalyst, only base and ligand is good enough for this novel or innovative synthesis of this heterocycle. And as you see, the advantages are this is a metal-free. The base is having only using the base and very cheap starting material. This is cheap and this is cheap. You mix these two only in presence of base, and you form this heterocycle. Okay. So we did the substrate scope as usual. So I will not spend time much on this. We have a big library. I'm showing you only few. And one notable thing here. Reaction here got a mixture. Okay, so the two regioisomers, the different you see, the methyl group is here, and in other case the methyl group is here. Okay, so in the manipulation differences in other things are same, but this methyl group you see with the same starting material, we got in two different position, 2-to-1 mixture. Okay, this is also, of course, we got later on the explanation. I'll explain you in a minute. In next slide, I'll show you the mechanism. Before that, as always, some control experiment to get more information about the mechanism. So what we did, instead of taking the alcohol, so as you know, so we were taking alcohols initially. So this is not starting materials. So then what we, instead of alcohol, we took a ketone, okay, benzophenons, okay, benzophenon we took, and the same, we got also the product, 81%. So that means, so benzophenon is one of the intermediate in our reaction. And then what we did in presence of tempo. Tempo, probably some of you know, this is a stable radical is and also used as a radical scavenger. So whenever the reaction, any reaction goes via radical pathway, and if you add tempo there, tempo will just scavenge that intermediate radical and then it will stop the reaction. So exactly same happened. We got very less than 5% yield. So basically the reaction tempo act as a poison for our reaction. All right. And last but not least, we checked that if you take the alcohol as standard reaction condition, it's forming H2O2. Okay, in H2O2, the reaction method for H2O2, we did that, and then we found that H2O2 is forming in our reaction. So these are the information we got from the experiment. Now the real mechanism. So what's happening here? We use the ligand. Okay, so we use this ligand, phenanthroline and potassium triterbutyls, which is. So what's happening here? So potassium is a cation, and this is a good ligand. It's forming a complex with the potassium, and tertiary butoxide is the counter anion. Now it is known that if we hit this complex, then this potassium tertiary butoxide and transfer electron species. Okay, once you form this, transfer this electron, then it's form radical cation, and this species becomes radical anion. Okay, and once this form a radical anion, this becomes a very electron donor. So this is called organic super electron donor. This is very good electron donor. This is forming in the background in our reaction. So then what's happening? Here we go. So we used an alcohol. Okay, so in presence of, we did not, in this case we did not use any inert atmosphere, no argon, no nitrogen, air or oxygen. Okay, so in presence of base and oxygen, this alcohol is getting oxidized to ketone. We started with ketone and we got the product, that means this is the intermediate, as we said. So this is forming this, and we have amine here in the mixture already. So once we form amine and ketone, it will of course condense and form this imine. Okay, once you form this imine, and then we have this organic super electron donor already present in the molecule. Then there is one single electron transfer, ACT means transfer will happen, and this will go because of the imine, this becomes little bit electron deficient. It will give this electron to this in the LUMO, and once you push electron here, this carbon iodine bond is bit labile, homological breakage of this from the I minus and radical. Okay, so once this form, this aryl radical is reactive, it will intramolecularly cyclize and form this new radical, and ultimately this transfer one H dot molecule and form this product. The re-aromaticity here, nothing else. And as you remember, I told you formation isomer. So how that is possible? Because after this radical, this case, in normal case, is forming a new carbon-carbon bond here, a six-membered ring directly. Now a five-membered ring also here, because it's a double bond, right? The radical can add here and add here also. If it add here, then it go via this five-membered intermediate, and there is a little bit rearrangement here, carbon breakage, and you form other. You see, in this case, R is here in the para position. Now, because of this rearrangement, our group shifted to one step here, and you form ultimately the product, a double bond formation here. That is the heterocycle, targeted heterocycle. But because of the rearrangement, this R shifted one position. Just by proposing this mechanism, we also explain the formation of different. Anup, how much time I have left? Can I speak 7 minutes more?
Yeah, sure. You can continue.
Okay, thank you. All right. So this is the mechanism. Okay, so now let me tell you something which is new, and one master student did that, and I hope you will also like it. So far, so starting from the quinoline, benzoquinone, benzimidazole, and whatever at the end, the heterocycle I have shown. So everything is homogeneous reaction. Okay, so the homogeneous reaction means, so the catalyst the reagent, whatever we are using, that is soluble in the solution. Okay, everything soluble. And after doing the reaction, so what we are doing, we are sometimes quenching the reaction and then doing workup, and then a standard just purification using column or so, and then we are getting the product. And whatever catalyst we are using, are catalytic, right? So whatever catalyst we are using, so those are also soluble in the solution, and during workup or column, those just get removed. Okay, and we lost that catalyst. We can't really reuse those. So whatever you use, that is wasted. After one reaction, this is just junk. Okay, this get wasted. We can't really reuse. It's very difficult to reuse a homogeneous catalyst. So how can we reuse a catalyst? Okay, so from this thing, the concept of heterogeneous catalysis came. So heterogeneous means, in this case, the catalyst will not be soluble in the solution. It will remain as insoluble. Okay, but it will still do the catalysis. So, and the advantage is, so, and then after the reaction, so you get the product and everything, and that product and all the byproducts will be in the solution, and product, your catalyst will still remain insoluble, right? And you will do filtration or so, you will get back your catalyst very easily, and then you dry it up and then you reuse. Okay, so that is the benefit. And so we planned something more advanced. So what was the plan? So we thought, say, instead of filtration and everything, can we do one thing? We put some we make some magnetically active. Concept is, if you take one iron nanoparticle, so as you know, irons are magnetically active, right? So just think about an iron ball here. Okay, so if you just take an iron ball, and then our catalyst, as you know, the nickel or ruthenium, whatever. So this is the, so for example, the ruthenium. If we can put a ruthenium layer on this iron ball, but it's difficult that iron ball will not hold this ruthenium that's easily. Okay, so we need kind of glue to stick these rutheniums on these iron balls. So we plan to use silica. So there is an iron ball and there is a silica, and then we'll put this ruthenium catalyst on this silica bed. Okay, so as a whole, this will act as catalyst, heterogeneous catalyst, or catalyst nanoparticle catalyst. Okay, the advantage here, because you see, this is no such organic ligands are used here. All are kind of inorganic. Iron is inorganic, silica is, is like a sand, right? It's also not really soluble, something insoluble, and also some ruthenium catalyst put here. So as a whole, these things are like a ball, nanoparticle, nanoballs, and it will not be soluble in the solution. Okay, so what we will do? We will do whatever catalysis we want to do, and after that, we thought, can we use a magnet? If we put a magnet just to the one side of the pot, reaction pot, so what the magnet will do? We will just attract these nanoparticles at the side of the pot, and then what we will do? It will hold it, and we will just decant this solution. Another pot will get whatever reaction mixture, product, byproduct here, back this catalyst. So we will again reuse this catalyst. Okay, this was the concept. And one talented master student who worked in my group, now he is this Ashwin Chaturvedi. He is now doing PhD in US. So he did last year. So he took this iron 2 and iron 3 combination from this fast iron nanoparticle. Actually, we are not the first one. So he followed this reported literature preparing this catalyst. So first this iron ball or iron nanoparticle, then he put this silica bed on this kind of silica glue on this iron ball, and that ammonium trichloride catalyst, and it is embedded on this silica bed. As a whole, it becomes very good nano catalyst, insoluble heterogeneous catalyst. And we did one standard reaction. So what we took isopropanol, and the same concept I have already explained to you. This is a the lithium catalyst first form acetone in situ here. Okay, and in presence of base, it will undergo aldol reaction, aldol condensation in both sides. So this red part is from isopropanol, and this green part are coming benzaldehyde derivatives, and you see these nice molecules. Okay, so we prepared also with the ferro nicely, almost 80% yield he got. Okay, so this is the thing. So you see, previously it was a cartoon picture. In the real laboratory he did like that. So you see, it's still after the reaction is still insoluble, the catalyst. With the magnet he can hold it nicely, and then he decant this thing. You see, after this is nicely the reaction, we do the purification here, and this is, we get back this nano catalyst which we will use after just a little bit drying, and again you can put reactant and reagents and do the reaction again and again and again. So this is very efficient and elegant method to do catalysis. All right, Anup, can I do a little bit, or should I stop here? Because I think I talked too much. I was a little bit slow. I try to explain things.
Yeah, maybe you can continue for another 5 minutes. Is it okay?
5 minutes. Okay. So as I promised at the beginning, so chemistry part and other part, but I just showed the bonding hydrogen thing. And as I said, very quickly, I will go through these new things. This is the main focus of our research group now. So, and I'm sure for many of you, this is something new. So electrochemistry. So redox synthesis using electricity. Okay. So let me first tell you very briefly the general concept, and I will quickly show you one result that we got in the synthesis of couple of heterocycles. That I'll go a little bit fast later on, but for in this initial slide I will take some time, maybe 2-3 minutes. Okay, so what's happening here? Electrochemistry. Electrochemistry reaction mixtures are nothing but a cell. It's like an electrochemical cell. Okay, so which is, as you know, in electrochemical cell we have one anode, one cathode, right? Anode, one cathode, and anode is responsible for oxidation, always for oxidation. That's why I call anodic oxidation, and cathode is responsible for reduction. As you see, anode takes electron from substrate. That's why it's responsible for oxidation, and cathode gives electron to substrate. That's why it's responsible for reduction. Okay. Anodic oxidation, cathodic reduction, and as I already said it to you, focus of my research group is redox chemistry, reduction and oxidation. So this electrochemistry is perfectly fitting with my group concept. Okay, that's why we are focusing a lot now on this, and I believe this is the future. So you see, after a few years or maybe a decade, so it will be many of the important will use electrochemistry in a larger sense. Okay, and I hope our group will contribute there, definitely. So what's the general concept? So the thing is, if you take a substrate and put electricity and appropriate electricity, then this substrate can go to anode and gives, in other words, an anode can take electron from the substrate and form a radical cation. Okay, and this radical cation is reactive. Of course, it's a reactive intermediate, and just following your desired step, you can generate product. So starting from substrate to product, just by doing oxidation, you can do. Okay. In other way around, want to do a reductive transformation. So if initially the first one is oxidative transformation. Suppose you want to make alcohol to aldehyde or alcohol to ketone, right? So you can do that by using electrochemistry instead of using any oxidative reagent. Normally from alcohol to ketone, how we make? Using any oxidative reagent, right? Here, just by putting electricity, you can do that. Or suppose you want to reduce something, okay? Something reduced, suppose from nitro to amine, you want to reduce. Okay, normally what you use, hydrogen palladium or hydride source you use normally in classical case, but you can avoid those just by putting in an electrochemical cell that and take electron, and of course H plus is available there in solution, and it form this substrate minus radical anion, and then follow up step and form the product. As I said, from nitro to amine you can prepare easily using by reductive transformation. Okay, sometimes it may happen that direct oxidation or reduction of the substrate is not possible, some mediator or catalyst. Okay, so in those cases, so this mediator first get oxidized and form something a reactive intermediate, and then those oxidize or reduce those substrate which is reluctant to go to the anode or cathode directly. Okay, so there are many methods on this. So there are like tempo, DDQ, or so on and so forth. There is a beautiful review by Baran and co-workers in 2017. They wrote a review and a chemical review. Whoever interested in organic electrochemistry, I highly recommend to read this review. Okay? So then you will get the general concept and everything there. So what's our contribution? What we wanted to do there? So we wanted to make heterocycle. So as you know, so the title of this talk and the major focus of this talk to make heterocycles. Okay? So we thought to make using this electrochemistry 2 heterocycles. One is this oxazole, and another one is isoxazole. Okay? We also realize these chalcogens, this selenium and sulfur, these are very important functionality. We also thought in one shot we'll introduce these chalcogens also in the molecule, and we form this heterocycles. So this is the in one line our whatever methodology we developed using electrochemistry. We started with this okay, allyl amides and form this heterocycle oxazole. Also started with this beta gamma unsaturated oxime and form this isoxazole using electrochemistry. Later on, of course, I will show you the mechanism. Okay, but this is the one liner. So what's happening here? What was the concept here? Next slide, summarize. So we are using this dichalcogens, diphenyl diselenite, okay, and putting in electrochemical cell. So now it's known that this diphenyl diselenite will go to anode and get oxidized, just giving one electron. The selenium is in the same group of oxygen, is having lone pairs here. Okay, electron and form a radical cation. Once you form this radical cation, this is unstable. This thing, it will undergo cleavage. Okay, the selenium bond will cleave and form this selenium cation and selenium radical. And once this selenium radical is formed, it can again go to anode and get oxidized and again form another molecule of selenium positive charge, selenium cation. So the fate of the selenium cation. This is the other starting material, right? This unsaturated allyl amides. The selenium cation can go there and react with this double bond. It's similar to this iodinium, right? So if you add iodine to a double bond, what will form? This form a cyclic. This selenium also will form cyclic intermediate like this. Once you form this, you see now from here from oxygen 1, 2, 3, 4, 5. Okay. So this is nicely done. 1, 2, 3, 4, 5, 5-membered ring. So this is a electrophile, right? So nitrogen can push electron here, oxygen can come back and react here, okay, and form this 5-membered ring. So this is the new bond, and this open up here and put the selenium here. So by doing so, you see we are forming nicely this, activating this double bond and forming this heterocycle. This is the concept. For the isoxazole is the similar. I'll skip because I don't have much time. I will skip that. This is the substrate scope here. I will also go a bit faster. We really did a lot of substrate scope. I just shown you only very few. You see the yields, very good, 91%, all close to 90 and 80s, high 80s. And also what we did, instead of selenium, we could also use disulfide. Okay, sulfur also working. So sulfur we can also put and also form these oxazoles and isoxazoles. We really did a mechanistic study, but I don't think that we have time, so I'll skip these slides. We did control experiments and also this cyclic voltammetry. So cyclic in electrochemistry, we really frequently need to do this cyclic voltammetry to know the voltage, the potentials where the starting material will get oxidized and reduced, so that we can really plan things. Okay, so we really did a lot of mechanistic study, and we have now really good systems. Okay, so I'll just keep this because it will take a longer time. So ultimately, the take-home message is, after doing all these things, we really know how to dot and selenium plus, and correctly our group is really focusing on this. As I said again and again, this is the major focus of our group now, doing organic electrochemistry. And maybe in near future, I will tell you a whole lecture, 1-hour lecture on organic electrochemistry. We have developed really several methods, really interested on using this concept. Okay, so I'll stop here. And before stopping, of course, I thank my co-workers. So this is I'm really lucky, and to have this very talented individuals. I really did not get much time to tell the work done by Sonju and Devabroto. Okay, and then the Benzimidazole also Sonju and Somrat, and later on this fluoroalkyl things developed by Arun, who is a postdoc in my group. Yeah, and what else I see? Okay, so this one, the nano thing, as I said, Ashwin is not in this picture. He is the master student. Punuma helped him a bit. And the last part, organic electrochemistry. So Somrat took the in charge of that project, and helped by Mrinmoy, Kingshuk, and Devabroto. They helped him. And I did get a chance to tell about organic chemistry. Tonuma is exclusively working on that, and Kingshuk, who really started the organic electrochemistry in my group. Now many people like Minmoy and others, Lokikanto, all are working on that. And these are the master students. We are really having talented master students in IISER Kolkata, and they are also here. And also I did not get chance to tell about Atre's work. They really nicely developed another method of synthesis of quinoline, but by using iodine, using mechanochemistry. Maybe in some other forum I will tell you that. Okay. And of course, thank to the funding agencies. Without money, we can't do research. As you know, IISER Kolkata helped a lot, of course, and any project for consumable and instruments, and of course CSIR giving fellowship to many of the fellows here. And in IISER Kolkata, we are not only doing science, we are, of course, we have life after okay. So last year we visited Shangu Lake. This is the Shangu. We went there, and as you know, so this is my group there. As you know, this is our group logo, right? The Red Ox group. We did not get any Red Ox there, but we got one yak with red horns. You see, red horns, and my student really forced me to climb up, and then they took a photo. Okay, for fun. Okay, thank you very much. So I'll be happy to questions. Yes, thank you. Anup, over to you.
Thank you, Professor Sumonde Sarkar, for your very nice presentation, and especially your wonderful explanation about borrowing hydrogen and redox concept and electrochemistry. And I would like to congratulate you for your very recent achievements regarding polyfluoroalkylation and heterogeneous catalyst, especially the very difficult oxidation of trifluoroethanol. So right now we would move to the question answer session. I have a couple of questions for you regarding the synthesis of quinoline.
Right.
The mechanistic part. Can you please go back to that slide?
Okay, then I have to go to the presentation again. Yeah, okay. Right.
The mechanism of quinoline synthesis.
All right.
Maybe I can ask you the question here. You have shown two alternative approaches. One is the first aldol reaction, and second one is the first imine formation and then aldol, right?
Right.
Okay, and but I see that there is another alternative, the background reaction, the self-condensation between two alpha keto amines. Did you not observe this background reaction?
So you mean the self-condensation between these two?
Yeah, self-condensation.
Yeah, this is one possibility. So this is the trick here. The thing is, first of all, once we form this aldehyde, or ketone, the activity of imine, this imine becomes a bit low, right? Because group.
Yeah.
So the nucleophilicity of this amine is comparatively less than standard aniline. This is one thing. Okay. And the second thing is, even if we have some reaction, background reaction of self-condensation, but we are generating some water here. And this means it will form an imine, right? Imine, and this are generating some water there, and this imine formation, as you know, it's reversible. All right. So this is reversible. Even if some imine forms, then with the help of water, it will get hydrolyzed and give back this aldehyde. But you see, once you form this heterocycle, this is super stable. Okay, there is no other way that it will reach goes back to the starting materials. Yeah.
Okay.
So that's why even if the reaction goes in a wrong direction, it come back. It can rectify and then goes to the desired pathway and form quinoline. Yes.
Okay. And then what is the driving force for this oxamical step?
Driving force, you know, this is reversible. So even if I'm not sure which one is favorable, of course, this double bond is conjugated, probably it will form. But once you form this, as in the control experiment, we can see in the reaction is not really happening, only 50% yield, because as you know, this is the trans double bond, right? And it will far away from each other. Driving force, no, there is no such driving force, but this is reversible, right? So even if this is 90, suppose the double bond is more stable, and it's having 90%, and only this alcohol is 10%. Okay. Then also it can undergo this cyclization because it's now flexible. This single bond here is flexible. It can undergo this cyclization. And once this cyclization goes, that means this 10% is getting consumed. So Last-Atelier principle will force to regenerate this, right? So that's the thing.
Okay.
Yeah.
Okay. Okay. And regarding the control experiment, here you have prepared the intermediate, and but this intermediate you have added 2 mole% nickel and 1 equivalent of the base. But I really could not understand what is the role of nickel catalyst in this control experiment.
In this control experiment, actually, there is no role of nickel, to be honest.
Okay.
But
yeah,
we wanted to keep the reaction exactly identical. The reagent, whatever catalyst and reagent, exactly identical reaction. Okay. So our main motto or main target is to prove that this is the intermediate forming in the reaction, right? And we wanted to keep this thing identical to our original reaction, and we did that, and we formed the product. So we proved that this is the. If we vary something here, then someone did not add that. This is not the exact condition like that, right? So that's why. But as you said, so there is no role of nickel here because nickel is doing the dehydrogenation. There is no role of nickel here. You are right.
Okay. Okay. So another query related to the benzimidazole synthesis. Benzimidazole synthesis. Yeah, no,
yes, mechanism
no,
mechanism?
here.
Okay.
So here, what I see that you have restricted the chemistry with only benzyl alcohol, most probably because of feasibility of oxidation, right?
Yes, because we need benzyl alcohol. Otherwise, you see here, we are functionalizing everything. Yeah,
right. But what I want to know is that what is the versatility or versatility of this methodology with varying groups in the benzene ring of the benzyl alcohol? What I see that.
So as you,
yeah, but what about if there is a very strong electron donating or very strong electron withdrawing group?
Yeah,
like
here,
nitro.
methoxy we did. Methoxy we did. Yeah, nitro we can't really use because then nitro will also, it will form amine.
It will be reduced, right?
Definitely. Nitro, if you take nitro also in the alcohol part, if you take R
but
as R, it will also get reduced.
Will it be the same case if you take alcohol or ketone or ester moiety in the benzyl alcohol part?
Ester, no problem. I think we have taken ester also. I told you, we have done so many limited time only.
Okay, fine. Okay, thank you.
Yes.
So One more question from the participants part. By what experimental method oxidation state of a metal is confirmed?
There are different ways. So, for example, easiest way to just by doing UV. Just by doing UV, you can see. So, for example, known methods, known metals, like if the complex is known, suppose you have iron 2 and iron 3, or even different oxidation states. And if you have a for that, and each oxidation state will have different UV absorption. Okay. And just during the reaction, you take out some amount of the alicate and then measure the UV, then you can get the information. Okay. So for iron 2, will have absorption in one position, and iron 3 will have absorption in different position. These are known for a known complex, and you can just compare.
Okay. Another question is that, is there any possibility of formation of byproducts during electrochemical method?
Oh, definitely, definitely. So electrochemical method, there is one of them is to control the selectivity. You know, so you are passing electron, right? And electrodes are wide open for oxidation of anything, and cathode is a reduction of anything. So this designing properly and controlling the reactivity and getting the selectivity is the major challenge in electrochemistry. That's why many groups are being asked, and there is a high possibility of forming byproducts also, yes. But we need to develop methods intelligently, and so that we can minimize the byproduct formation for that. And Anup, for answering the previous questions, as I said, only UV is one of the methods, and there are many other methods to know the oxidation state, like because in some oxidation state the metals are magnetically active, right? EPR active, or some oxidation state not active. So there are many methods here.
So one question, Dr. Sarkar, I have a question that if it's in the previous slide, you start that one diamino compound converted to benzimidazole derivative, the cobalt hydride is formed through the cyclization. How will you characterize the cobalt hydride is formed, or is it absorbed hydrogen by its solid surface, or not, or is it inorganically formed COH2?
No, it's not inorganically formed. It's a very good question, actually. So to be honest, we did not characterize this hydride. So this is a bit challenging. This is really challenging because these cobalt hydrides with these ligand systems is quite unstable. Once it's formed in solution, immediately it will react with the nitro normal cobalt, okay, and gives back the hydrogen hydride. But there are some reports where we really specifically design the ligand system where the metal hydride is stable. There are some reports, not in our case. It's very transient and short-lived species here in our case. Okay, we did not really characterize this. And normal case, as you know, this metal hydride they can detect by NMR spectroscopy. This metal hydrides is really having delta value in the negative range. Okay, and those like that you can characterize. Or sometimes if it's really stable, you are lucky, you can get a crystal structure also.
Okay, so I see that there is no more question for you, Professor Desarkar. In that case, let me thank you once again for your most valuable time and for your nice presentation. Thanks a lot.
Thank you. Thank you, Anup, and thank you, everyone. So, and then so maybe in future we can arrange few more of these, so I can talk about other topics.
Yes. Sure. Yeah, I hope so.
Okay, then thank you.
Thank you.
Right. So
okay, this is
next presentation. Yes.
Yeah, sure. Okay, so this is the time to move to the second lecture of this technical session. I will hand over the platform to Dr. Biplav Mondal for introducing the next speaker. Dr. Mondal, please start.
Okay, thank you, Dr. Anup Biswas. Am I audible? Hello?
Yes, you are audible. Please continue.
Okay, I am Dr. Biplav Mondal, Assistant Professor, Department of Chemistry. On behalf of this organizing committee, I am introducing my friend Dr. Balaji Prasad Mondal. Dr. Mondal completed MSc from University of Burdwan, West Bengal in 2003. He joined BARC in 2004 from 47 batch of BARC Training School. He was awarded the PhD degree in chemistry in 2009 by Mumbai University in recognition of his work on high temperature ceramic materials for futuristic nuclear technologies. He did his postdoctoral research Hello. He did his postdoctoral research in development of new electrodes from lithium-ion battery at Wayne State University, USA. He was awarded DAE Young Scientist Award in 2012. He has been awarded membership of National Academy of Science, India, and also he has received DAE SSPS Young Achiever Award in 2017. Presently, he is involved in development of battery materials with higher energy density, power density, and long cycle ability. He has transferred the technology for synthesis of electrode materials for lithium-ion battery to different Indian companies for commercialization. Dr. Mondal has more than 60 scientific papers in the Journal of International Reputation. Dr. Mondal, now this platform is to you.
Thank you, Biplav. First of all, I really would like to thank the organizer for inviting me here. Okay, are you getting my screen? Okay, let me.
Yes, you
are getting my screen?
Yes. Please continue.
Okay. Thank you, organizer, for inviting me for this presentation. And I especially thank Biplav. We were friends in University of Burdwan, and we used to stay in same hostel. So today I will be talking on nanomaterials. It's a bridge between science and technology. Okay, I am talking just before lunch, so some of you may be feeling tired or hungry. So whenever you will feel that I'm getting too bored, means I'm making you bored and it's too long, just give me some indication. I will finish it off. Okay, so this is the materials age. If you see that first, we studied in history that Stone Age is 2 million BC. Then came the Bronze Age. Then Iron Age. Iron Age was in 1200 BC. Then Concrete Age, that was in 200 BC. Then came Steel Age in around 150 years back. Then you all know that Silicon Age, this computer technology, semiconductor. Then now we are going slowly to this miniaturization of the things began in 1990, around 30 years back, and we are going towards the nano age. Now, in last 30 years, if you see, there are a lot of breakthroughs in materials. So whatever I talked in the last slide, you see they all are materials. Either it is stone or it is concrete or whatever you say, or nanomaterials. Basically, the materials takes the center stage. In last 30 years, there are some breakthroughs in material science. In 1986, it was high temperature superconductor, and then it got Nobel Prize in 1987, and then fluorine and nanotubes in 1990 or 92, around that. And you know that fluorine Nobel Prize was given in 96. Then mesoporous solids, my previous speaker was talking on catalysis and all. So for catalysis, mesoporous solids are very important thing. So that was discovered in around 1992. Then CMR and GMR material, basically colossal magnetoresistance or giant magnetoresistance. Means just with change in slightly magnetization, the resistance changes huge. That those are the called the CMR or GMR material. That also got Nobel Prize in 2007. Then conducting polymers. Mostly we may think that these polymers made of organic polymers. Why they should conduct? Because they are mostly non-conducting material. Because our polythene and all you have seen, they are the insulator material. But in 1980, it was made conducting polyaniline, polypyrrole, they are made, and they are the conducting polymers, and that also got Nobel Prize in 2000. And graphene in 2007. Graphene is basically single layer graphite. We know that graphite is some composition of some layers of carbon, and if I can remove one layer from there, then we get the graphene, and its conductivity is very high. Conductivity means electronic conductivity is of two types. Either electron can move or the ion can move. Let's say in our copper wire, it's the electron move. Or let's say we have sodium chloride solution, their ion moves, their electron doesn't move. So in solution, or in case of there are some solids also where the ion can move, so they are the ionic conductor, whereas where electron move from one end to another end, they are the electronic conductor, in very simple language. Now you know this last year we got this lithium ion battery got the Nobel Prize. Lithium ion battery basically it is also part of material science, material chemistry. Earlier there was a strong boundary between I would say physics and chemistry. Then slowly the material science, material chemistry came into the picture, and that is taking the lead. And nanomaterials research it started in mid 90s. Even though the science of nano or the term nano started in mid of 1990. Even though the science was
Dr. Balaji, sorry to interrupt you. Hello.
Yeah, please.
Do you have slides or presentation?
Yeah.
Do you want to share it later, or because we cannot see the presentation?
You cannot see the presentation?
No.
Oh,
you have to share it.
That's what I was asking. I'm sorry. Really, I'm sorry. I was thinking that it's shared. Now you can see.
No, only we can see your background, and
then how to share? Because present now, I click the present now, your entire screen. Then I click on the screen, and then I am sharing, and now my screen. Are you seeing my screen? Are you seeing my screen?
Yes, it is loading. Just a minute.
Okay. I thought
no. It is. Yes, it is now visible.
I'm really.
Yeah, no problem. Maybe you can go to the full screen mode.
Okay.
Now you can see the whole
screen. Yes.
I'm really sorry. I thought it is already shared. There was some link problem.
Please continue.
Yeah, what I was telling that in 2019, just last year, Nobel Prize is given in lithium-ion battery. This is also material science, material chemistry. Typically this material chemistry is a relatively new subject. Earlier we had this organic, inorganic, this kind of demarcation we had. Now the material science, this is basically part of some from organic, some from inorganic, and physical also. So the point is that this material chemistry or material science, or you can say material physics also, is taking the lead now. So what is this nano? Okay, nano is the part of material science, material chemistry. Nano, it's a Greek word. It means dwarf. Its height is smaller. So let us try to feel how much is a nanometer mean. 1 nanometer means 10 to the power minus 9 meter. Okay, in the left side you can see that we are showing a small bird, and its size is a little less than 100 mm, hummingbird. And then you see the top of the pin is showing that's around 1 millimeter, and in our red blood cell there's around 10 micrometer. And you see the virus. Now it is the time of virus. He is taking the central stage. The virus around 100 nanometer. I think coronavirus is around 300 to 400 nanometer. And if we still go lower, then one DNA, and they are in that 1 nanometer size. And when we are go to the atomic scale, they are in the angstrom. They are the 0.1 nanometer. It's the size of, let's say, sodium, potassium. They are around 1.2, 1.3 angstrom. And right side is the more clear picture I am trying to show. I am trying to it's that if we consider the distance from Calcutta to Delhi or a little bit lower, it's around 1,000 kilometers. 1,000 kilometer means 10 to the power 6 meters. So 1 millimeter and 1 millimeter and the distance between Kolkata and Delhi, you can think about the 10 to the, basically that is 10 to the power 9 times bigger. So if you just think in reverse direction, that 1 meter and 1 nanometer has the same radius. So just you imagine how small I am talking about. So the human mankind, we knew that 10 to the power 21 meter is the size of Milky Way, and the quarks, the elementary particle, its size is 10 to the power minus 6. So our knowledge, the mankind, know this big scale, and some nanometer comes somewhere in between, kind of here. Okay, so that means it's 1 nanometer. So is the nanometer is very new thing to us? No, nanometer, the term nano may be new to us, but it has historically we knew it. The bhasmas, you know, in Sarna bhasmas or the Chandi bhasmas, means Rupa bhasmas, is the silver bhasmas or the gold bhasmas. Those are mentioned in our ancient Vedas. They are the perhaps the first nanoparticle reported somewhere. And this Bhasmikaran process perhaps is the first process to make the nanomaterial. Nanocrystalline gold, silver, those are described in Ayurveda since ages, in history also. So I will show you one slide also. And in the Chinese history also, not Ayurveda means it basically it is Indian history. And in Chinese also, this gold, colloidal gold are used as medicinal, as medicine. These reports are also there. You know, this Tipu Sultan sword. Hello? Hello, any problem? Hello? Am I audible?
You are audible.
Yes,
Please
yes.
continue.
Yes,
Oh,
yes.
okay,
Please continue.
sorry. Okay. The Tipu Sultan sword, it was very powerful sword, and we have heard about this Damascus sword. Damascus is basically the place near Syria and Iran and Iraq, that place. So those sword people say used to be the very strong sword in history. And Tipu Sultan sword was from there, and many other people took the sword from there, and perhaps a Mughal also took the sword from there. But why those swords were very strong on those days? They used to take this sword from the material from India only, and they used to make the sword there and used to sell to different parties. So in 2006, there was one study on Tipu Sultan sword, and it was found that their carbon is used in less than 1% in making those steel, and that carbon nanotube. And those are the carbon nanotube. And carbon nanotube is really having huge strength, mechanical strength. So those are used in those swords. So in a single sword, you have heard they could cut the head of a horse. So this concept was known in those days also. And this one picture, it's from Lycurgus chalice. It's in 5th century AD. So it is reported that in these glasses also, gold nanoparticles were used in the ratio gold and silver. Silver and gold ratio was 14.1, and you can see there luminescence from outside and inside. And the first, actually, till that time, the science was not that much structured. It was not institutionalized. It was mostly on the garage or somewhere people just used to do it discreetly. No meeting, no structured way doing science was there. So first, Professor Richard Feynman, that great physicist, he got Nobel Prize in 1967 or 69, I think. So in a meeting, he was saying there is plenty of room at the bottom. He's again and again was saying there is plenty of room at the bottom. Means when we decrease the size of any particle, we reach to the very lower size, and there are lot of property changes. And when he was talking to the addressing to the audience, and they're saying, okay, I have heard about the electrical motors. They are of the size of nail of our small fingers. He said, no, still much more lower. And they said, maybe Lord's Prayer can be written on the head of a pin. He said, no, that's still lower than that. Maybe whole encyclopedia can be written. Old Mahabharata can be written just on the tip of a pin. It is that kind of technology is coming in future. So this is the I got from Gold Bulletin this slide, and in those days, in the gold nanoparticle was synthesized in this process. Gold and mercury and sulfur they are used, and you can see the whole process. So using the cow dung, the heating process, heating source was cow dung or wood only, not the modern days heater or oven kind of things or the furnace kind of things that are available. So if we nowadays, if we prepare the gold in same process, we saw that the gold nanoparticle, whatever we get, that is around 50 to 60 nanometers. So whatever they used to prepare, perhaps unknowingly, they were the gold nanoparticle. In 1857, it is very interesting year for us, as well as in India in scientific history also. In 1857, you know, the Sepoy Mutiny was there, and Mangal Pandey was the leader. And in the scientific era also, in the scientific domain also, Michael Faraday, he first made metal at divided step. He did not mention about the nanoparticle or something. He said that something kind of colloid, and this is kept in on British Museum, in London. And now also, see, it is done in 1857, so it is around 150 years, 50, 60 years. So still it is stable. So this colloid is stable. And he prepared in those days, and he prepared using carbon disulfide in this HAUCl4, phosphorus and carbon disulfide. And nowadays we don't prepare in this way, we prepare in other way, and we could also stabilize. Why the nanoparticle stabilize? Because nanoparticle, the overall surface charge is very high. Therefore, they will always try to agglomerate. But if some capping is there on nanoparticle, so then they will not feel to come each other together. Some early papers around 100, 110 years back, Paulo, he discussed about the possible change in physical properties of some materials as a function of size. What he was mentioning that if we go really low in particle size, physical property will change. Physical property means the melting point, physical point, magnetic property, catalytic property, electrical property, the semiconductor band gap, they may change. And same in 1910 also, Lindemann predicted that there will be a drop in melting point if we downsize the particle size. So in 1980, in fact, in that time also this nano term was not there. And mid-90s, these nanomaterials, research in nanomaterials became very popular, or you can say fashionable also. And in that, by that time, AFM, atomic force microscope, then STM, then TM, transmission electron microscope, they started to come in the market. And actually, TM is discovered earlier also, but people started seeing those things, and then they see that nanomaterial can be prepared in lab also. The nature is making since ages. So what is the special feature of nanomaterials? When the particle size becomes low, basically a lot of particles come to the surface. So, and in a 2 nanometer sphere, around 60% of atoms will be at the surface, and it will have size. And the surface atom will have more reactivity, and there will be some unsaturation bond in the surface atom. Dangling bond will be there, and there will be a lot of vacancies, and the surface energy will definitely be modified. So the total feature of the material will change. When we decrease the particle size from millimeter to micrometer, there is no change in physical property as such. But when we go from micrometer to nanometer, lots of changes we observe. That physical properties like microstructure, melting point, hardness, and chemical properties like structure, catalytic activity, sensing properties, the electronic property, they change. So there are a lot of uses in. Now I'll talk about these nanomaterials. Really, these are. Then what is the new? So they can be used in healthcare, energy conversion, then potable water, sensors, cosmetics, and environment pollutant remedies and cosmetics. You know, these lot of cosmetics. Titania is used, TiO2 in nano form to protect it from UV light. And how these materials are prepared in general, there are a lot of process. I'll just include one or two to explain it. Basically, I am focusing this presentation to the students who would like to pursue their career in material science, especially in nanomaterials, so they may find it more interesting. And so there are several approaches. First is we call the physicist approach, and second we call as the chemist approach. And there is another option that is called the biologist approach. Physicist approach means the top-down approach, and chemist approach is the bottom-up approach. So in a nanoparticle, there are few blocks are there. You can think in that way. That in when we is a chemist we make we are very we really love to make a solution, and from the solution atoms they build they love each other and they come together and they build these are the building blocks and they stack together and we get the nanomaterial. Whereas the physicists, they do not like this chemistry. They sometimes, not all. I know some physicists, they are really excellent, and they prefer to break a big chunk and they want to reach to nano size. So that is also possible. In chemical method, so there are some combustion processes, hydrothermal method, then template method, and so on and so forth. Physicists also laser ablation, then CVD is there. Then there is one process called biological process. This, our fungus, bacteria, they can also make nanoparticles. Basically, but if we think really a little deeper, whatever we say in this biological process, basically they are chemical process only. This bacteria and viruses. Viruses, I don't know. Bacteria and fungus, they have different kind of groups in that, different kinds of organic chemicals in them, and they really make the synthesis of nanoparticles. We know, especially in the college, I'm sure that nowadays also you teach this synthesis of, this aldehyde test, the silver ammoniacal silver nitrate, and that we get the silvery color on the side of test tube. I don't know whether it is in syllabus now or not, but when we used to study BSc, this was there. And those are basically silver nanoparticles. What we take, silver ammoniacal silver nitrate, and we add the aldehyde, and this aldehyde reduces silver nitrate to silver nanoparticle. And in inorganic lab, we used to make iron oxide, ferric hydroxide precipitation, copper hydroxide precipitation for separation and all. I think this may be there in nowadays also. If we check them using TEM or XRD, or basically if we characterize them, we will see that they are also nanoparticle. But we did not know in our BSc days that they are the nanoparticle. So their surface area is more, and I'll talk about this laser ablation. Physicist prefers that in case of laser ablation, there is a vacuum chamber, and on that target, basically a laser falls on that. It's ablates. Ablation means if we simply heat is a then slowly evaporation takes place. So that is more of equilibrium process. But if we ablate, so it is a non-equilibrium process. By that also different kind of nanomaterials, especially oxide, tin oxide, titanium oxide could be prepared. However, there in case of physicist approach, this control on morphology and all are really tough, and the total setup are costly. Really, these will be some multi-crore business. So it is difficult. I mean, a cost affair, and you have to know a lot of physics in that. Whereas chemistry approach are relatively easier. Mostly we take these metal oxides, alkoxides, and we make a sol, and then we condense them, and we get gel. Gel, you all know, it is a 3D structure. If we can, uh, if we heat them, this gel, then we get the highly dense material. These are the zero gel, and if we selectively remove the liquid part, supercritical extraction, then we get the aerogel kind of things, and they are the high density, low density material. And how do we, chemists are very smart. They can really control the particle size and shape. There are a lot of shape directing agents. Size can be controlled by suitably choosing the property of the additive. Like if we take this any gold or silver salt and we add sodium borohydride, that is a very strong reducing agent. And by using the citrate, it inhibits the particle growth. It can, yeah, the silver particle or gold nanoparticle, and we can get spherical particles. And from that, if we CTAB, CTAB is a, what's that, micelle. Using that, we can ascorbic acid kind of reducing agent. We can really make nanorod. There are a lot of methods, lot of processes you will see in the present literature also. When I was making the slide, I saw some beautiful pictures. I did not put in this presentation, that how many people are doing controlling the shape and size of the particles and the morphology of the particles. And I'll be talking about the combustion synthesis. What is combustion synthesis? It is very fast. Within 10 minutes, reaction is over. We have to take some metal nitrate, metal oxynitrate, and some fuels, hydrogen, urea, or glycine, this kind of fuels, which basically we need a material where nitrogen is there. Nitrogen is not necessary, but it should be able to make chelate with the metal ion, and then that has to be heated. So once the aqueous part is removed by heating, and then the ignition temperature will reach, and suddenly there will be violent fire inside the beaker, and we will get the metal oxide. The problem with this is that it has no control. Mostly we do not have control on shape and size of the particles. You see in this picture, you can see in your Google also. You can Google. You will see in the YouTube how we make the auto ignition process, this combustion process. These are the metal nitrate solution you can see, and putting in the beaker. You see that within the beaker fire is there. You can see in YouTube. Now, once this material oxides are formed, these oxides still reaction may not be 100% over. There may be some unreacted nitrate. There may be some unreacted carbon. So what you have to do, you have to calcine them. Calcination is basically removing the impurity from the product. And mostly we prefer heating it at 500 to 600 degrees centigrade. And the bottleneck, the problem with this synthesis process is that mostly we will get the higher oxidation oxide, and oxide. We'll get the titanium oxide, TiO2. We will not get Ti2O3. Then in the next step, maybe we can reduce using hydrogen flow. We can get Ti2O3, or cobalt oxide. At higher oxide, we will get things like that, like cerium oxide, CeO2. We will not get Ce2O3 by simple combustion method. Now, as they are thinking, okay, we can prepare this material, but how really these materials look like? How to see them? So what to do? So my dear students, you can. There are a lot of techniques: diffraction technique, microscopic. Sorry, I forgot to say microscopic and spectroscopic. Then composition characterization. Compositional characterization is not to see the nanoness of the material, but yes, one nanomaterial is there, and if you have to see really there is phase pure or something, let's say I have titanium oxide or anything else is with it, that we can separate. And the diffraction techniques are there: X-ray diffraction, neutron diffraction, electron diffraction, then SAX, SAMS, which is small angle X-ray scattering, then small angle neutron scattering, microscopic technique, SEM, scanning electron microscope, and EM are there, and there are a lot of spectroscopic techniques are also there. So, and TEM, it is Ernst Ruska, he discovered TEM in 1931, that was used for detection of nanoparticle. Now, how the surface area changes, especially if the student, you may like it very much. If I have a cube of 1 centimeter length, then surface area will be 6 centimeters square. If I break it into in some method, some, let's say, imaginary method, to 1 nanometer, basically 10 to the power minus 7 times decrease in the size of the cube. So there will be 10 to the power 21 number of cubes like this, and the total surface area will be 6 into 10 to the power 21 nanometer square, and that is around 6,000 meters square. It's around the size of a cricket ground or a kind of a football ground. This is how much increase in the surface area. And catalytic property, especially the heterogeneous catalytic property of material, hugely depends on surface area. But yeah, there is a problem. It's not that all the area will be available. There will be agglomeration. There are a lot of surface area will not be accessible by the gases, the reacting gases. Anyway, so what are the usage of these nanomaterials? Okay, we made it. Now what next? So there are some. I have picked up some nanomaterials which I myself have used, and or some of my friends have used those nanomaterials in BRC also. So that a few of them I will present, and I have taken some from internet also. So nanomaterials for societal application. So we make them using the surface modification, morphology tailoring, or crystal structure. Basically, we are crystallographic people, so we know how to play with the crystal structure of particle and how to modify the morphology for different properties. Surface can be modified. That also we do. Now I'll talk about the nuclear medicine. You know, the BRC being a DAE unit, the DAE is Department of Atomic Energy. I'm from here. So here all the nuclear medicine India basically BRC provides in all the hospitals. So you know that element technetium, just after the molybdenum, the technetium element is not a naturally abundant element. It is a synthesized element. After 92, we know that 92 elements are naturally abundant, but really technetium is not. It's out of the league. So how it is? How we get it? In the nuclear reactor, we after the fission we get 99 molybdenum, and if it releases one beta particle, then it goes to, then we get 99 technetium, and that 99 technetium quickly transformed to ruthenium. Now this gamma, which you can see the right side. Oh, I'm sorry. This 6 hours is its half-life, and this half-life is suitable for cancer diagnosis or the cancer, in some cases also therapeutic purpose also. And technetium has very versatile coordination chemistry, so quickly it can be bound with the suitable ligand. Now the point is that in a generator, so we need a generator. What is generator? Generator means something is getting generated. So from molybdenum, technetium, 99M technetium gets generated, and we need that 99M technetium. So it's like milking the cow. So 99M is the parent. Sorry, 99 molybdenum is the parent, and 99M technetium is the daughter. So we need, our aim is to get the 99M technetium. That should be free from molybdenum. So you have to separate it. So in a solution, how to separate it? So we need a column, and in that column, some inorganic column is important. Is used to separate this 99M technetium, and I show you. And in this case, continuously, molybdenum is giving continuously 99M technetium. So where its use is, I have already said that cancer diagnosis therapy, not only cancer, there are other diagnoses also technetium is used. So we use some sorbent material, so that the particularly one of them, either molybdenum or technetium, should be absorbed, and then it can be the rest one can be thrown off or used. So presently, I am saying this is a sorbent material. This zirconium oxide. Hello, sorry, zirconium oxide nanoparticle or the titanium oxide nanoparticle, that is used as column. So what is the how it can be used? Molybdenum has a very beautiful chemistry that it is mostly polyanionic. It stays in polyanionic form, so it is more negatively charged. Whereas this zirconium oxide nanoparticle or the titanium oxide nanoparticle, their surface charge is mostly positive. Not mostly positive, it is positive. Its zeta potential is positive. That's why molybdenum will get attached into that. Molybdate anions will get attached into that. And whenever this molybdate anion will generate technetium, so that technetium, its surface charge is not that much. So that can be eluted using proper elutant. So this is the way we separate this technetium, 99M technetium in India. And earlier, this alumina was used. You can see in the left side graph, alumina, its efficiency is really low, whereas this zirconia and titanium oxide, they have really high efficiency. And presently, these are now used in practice in Tata Memorial Hospital in Mumbai. And this technetium, the separated by BRC method, that is now applicable to the patients also. And around 40% patients are getting this medicine. Now we'll talk about the use of nanomaterial in lithium-ion battery and fuel cell material, hydrogen production, supercapacitors. They are basically energy-related material, either energy generation or energy storage, or energy conversion. Fuel cell material, I say, is more of energy conversion material. Lithium-ion battery is energy storage material. Supercapacitor is storage. Hydrogen storage is there. Production is there. So their nanomaterial has huge role. So this is the SOFC, solid oxide fuel cell. So what is solid oxide fuel cell? Solid oxide can also conduct the ions. I'll spend little time here to explain it, and maybe I'll cut some time in the later stage. At the center, it is kind of a battery cell. Cell and battery, basically, they are of similar meaning. Basically, there is a little difference. There are, if number of cell increases, a couple of cells together is battery. So cell into n equals to battery, you can say. N number of cell gives battery. In this, say that YSZ is named as electrolyte. What is YSZ? YSZ, yttria stabilized zirconia. Basically, yttrium oxide is doped in zirconium. Zirconium oxide is ZrO2, and if in ZrO2, if we can create some vacancy by doping yttrium, then it will form oxygen deficient ZrO2, and in that the material will conduct oxide ion, but not at room temperature, at relatively higher temperature. What is the temperature? In 1000 degrees centigrade. But 1000 degrees centigrade is not easily available, because then if we have to make this 1000 degrees centigrade, that itself is energy intensive process. But anyway, and once the reaction starts, then it itself generates heating, and that can be used to sustain this process. And this is the cathode. Cathode means where the reduction takes place. And LaMNO3, basically doped LaMNO3 is used. In very simple way, it is basically reaction between hydrogen and oxygen forming water, and the energy, whatever is released, delta G, that is converted into electrical. So in SOFC, we have some components, electrolyte, obviously. You can see this is simply a kind of a battery, not battery, but kind of a battery. Electrolyte is there, cathode is there, anode is there, and interconnect. For the time being, let us forget this interconnect. So cathode, anode, and electrolyte, but all are solid. Generally, we are habituated to visualize electrolyte as liquid, because in liquid the ion mobility is very high. But in this case, it is a solid material. That's why we need higher temperature, so that the ion can move a little faster. And the electrolyte has some criteria that it should be highly conductive and it should be dense. Now, once if we need, it should be dense. Now, how can we make dense? So we have to make nano. Then only we can make dense. I can give one analogy. Like, let's say if I have a packet of stone, then if we put really big stone, then there will be a lot of spaces in between the stones. But if we crush it into sand, sand and then into dust, then the density will be very high. Why density is important? In the earlier slide, I was showing that oxygen and is fed in oxygen gas is fed in this side, in this cathode side. That should not flow to that side. That the oxygen, molecular oxygen, should not go to that side. It should be called oxide ion, and then oxide ion can only move from one end to another end. In another end, nickel YSZ is there that gives hydrogen ion. Here I have given another example, but that example is also true. So that hydrogen plus and oxide ion minus, they will react each other and will form water. And the cathode should have high electronic conductivity as well as ionic conductivity is also required. In this case, porousness is required. So again, the role of material science, again the role of nanomaterial is important. You see in this porosity column, I have written that porosity is around 30 to 40% is required, and anode is also of similar feature. And TCE is the this thermal expansion coefficient. Actually, it is TEC. Thermal expansion coefficient. They should match each other, because at high temperature, one expands more and another do not expand in that extent. So there will be some mismatch and there will be mechanical failure. So the matching is very important. Now, how to make this interactive? Whenever we have to make active, whenever we have to make the dense pellet, dense material, so the material, the powders, they itself should be interactive. Sintering means densification. So we should be able to dense them. Now, if a particle, if its surface is having unsaturation, so another particle will come and at high temperature, they will react, will form neck, and densification will take place. That's one point. So surface unsaturation is required. Small particle size should be there, and large surface area, obviously, that will give us large surface area. So then only we will reach to the dense particle. I have you can see the SEM picture. You can see that the particles are close together. There is very low level of vacancy, and here we can we could reach around 99% of theoretical density. And these kind of materials are required for electrolyte. And now I'll come to, okay, I missed a slide here. In case of anode and cathode material, we need the porous material. So this feature is not applicable there. So there we have to add some pore former like carbon and all. Whenever carbon is there during the synthesis, and if we heat at high temperature, that will form carbon dioxide and will go away. So obviously there will be some pores. Now, energy storage devices. There are three types of energy storage material. One is the battery storage material. Battery is an energy storage system, and then supercapacitor is there. Then we have hydrogen storage. Hydrogen is really of a great material. The energy, because it is the smallest element, the lightest one, and its energy density is very high. And now I am talking about the battery first. In a few days back, I was talking in another place, and there my topic was battery. And this in battery, in the first or second slide, I was mentioning that last year, 2019, Nobel Prize was given to Professor J.B. Goodenough, Whittingham, and Akira Yoshino. My respect to these three gentlemen. They changed the world, so they brought a revolution in this research. So I would like to spend some time with them. This J.B. Goodenough is an American scientist. He is now 97 years old. He was dyslexia he had dyslexia problem when he was a kid, and then he went to Yale University. Then he participated. He had to participate in Second World War to earn money because his parents really did not look after him. And then around at the age 40 or so, then he again come to science at the age of 40. Generally, people start at the age of 25, 20, 25. So, but still, since then, he had done really lot of work, not only in battery material, in magnetic material, and others also. And this second gentleman, second picture is M.S. Whittingham. M.S. Whittingham is the first person who talked about lithium-ion battery. However, his battery was of the low voltages, and the concept good enough to and good enough design new kind of material in those days in 97, I mean around 75 to 80 in that time, and that was the cathode side. And Akira Yoshino did the anode side. There was one professor from Bell Lab, Professor Samar Basu, and there are some more people also. I don't know why their name was not in the Nobel Prize list, because in the same year, that was 1983, they discovered this. I mean, Samar Basu and group discovered that graphite can be used as anode material, and Akira Yoshino also said in 1983. But I don't know in what is the exact month. Definitely, Nobel Committee has looked into this, and maybe Akira Yoshino is the first one. But anyway, that's not the point of discussion now. So I'll talk what is the battery and how where the nanomaterials are used in battery. In batteries, this is basically we very simply, but we all have our mobile or laptop. There we have a battery, and battery is the energy storage system. Chemical energy, we store chemical energy. I mean, we extract electrical energy from chemical energy, and there are two types of battery. One is the primary battery, another is the secondary. Primary battery means not rechargeable, like our clock or our remote control we use and so. And secondary battery, which is rechargeable. That is in our mobile and laptop. We do the recharge. In lithium-ion battery also, it's the rechargeable battery because we recharge it. And there obviously there is an anode, there's a cathode, an electrolyte, and separator. A separator. In this case, the electrolyte presently in our mobile, that is a liquid electrolyte, and that's why we are a little worried. Or you have heard this electrolyte they've asked also, and basically some organic solvent is there that gets evaporated and internal pressure increases and that bursts. So when we use the battery, basically at that time, that is a spontaneous reaction, and this delta G equals to minus NF, and the delta G is negative. That's why the reaction is spontaneous. When we do the charging, we force the system to reaction to go in reverse direction. That's why that in that case, that's why we put the charging. And in this, I will talk about this, how it in this diagram. I am showing how this reaction takes place. The reaction at the electrode takes place. You look at the cathode. Lithium cobalt oxide is the cathode. Okay, in case of lithium-ion battery, my previous speaker was talking about the electrochemistry of organic molecules. And yes, this cathode and anode, by definition, the anode is where oxidation takes place, and cathode is where reduction takes place. But in case of rechargeable system, it is really confusing because during the charging process, whatever happens during the discharging, just the opposite thing. So whatever was cathode during the charging, that becomes anode in the time of discharging. So initially, when I also started working in this, I used to get confused. But anyway, with time, it becomes much easier to understand. So how it goes when we do the charging in our battery. So we have this lithium cobalt oxide. The left side, you can see this is the lithium structure of lithium cobalt oxide. Some green color polyhedra is there and some golden lithium atoms are there. So that is the lithium cobalt oxide. So that is the anode cathode material. And this cathode material, the requirement is that the lithium ion channel should be there so that lithium ion can move in and out. So then only the diffusion will take place. And the right side is the graphite anode, and you all know, especially those who are from chemistry background, that the graphite is having it's a layered structure, and there are some interlayer spacing, and those interlayers, within these layers there is a spacing, and some atoms can be pushed. It was not known before 1983. It was the discovery of Professor Thamar Basu. Anyway, the present day batteries, this anode material, graphite is used as anode material. So what happens during the charging process? The lithium atom, you see the lower arrow, whatever I am saying, the lithium atoms comes out from the lithium cobalt oxide and go to the carbon, the graphite, and it sits in between the interspacing, and there is one separator is given so that the cathode anode do not touch each other in the frame. So what happens? You can see that lithiated lithium 1 - 6 COO2 forms. It means some lithium has gone out from the cathode, and where that lithium has gone, that has gone to the graphite side. And when we are using that means when we are charging it, so those lithium which were sent to graphite, they come back to their original home and they find very comfortable there. So now you see the one point, whenever lithium ions are extracted from lithium cobalt oxide, definitely there will be shrinkage in volume of the crystals, and whenever this lithium will go inside the graphite interspacing, then the spacing between the graphite layer will increase. So there will be some mechanical stress. And in long time, that's why our mobile fails after a couple of years, 4 years. You see that, oh, battery is not working. Basically, due to this mechanical stresses, strains, the kind of a breathing thing takes place, and it pulls out from the current collector. Now, so what is the criteria that electrode should have? Electrode basically, that is intercalation, deintercalation should take place, and it should be electronic conductor, and volume variation should not be high. So now, so where is the role of nanomaterial there? That's the theme of my talk. So whenever we have a big particle, big chunk, let's say macro particle, then the coming out of lithium ion from the center of the particle to the surface is really difficult. The lithium ion has to walk a long distance. But if the particle size is smaller, then it can time will be lower. It will take less time. So conduct lithium diffusivity will be high in case of nanomaterial. That's why we are looking for this nanomaterial. I tell you, this lithium ion battery technology, these new things were developing in 90s only, but there was no boom in that time. After the advent of nano and carbon science, then only this science go faster. I'll put some more examples. This is lithium iron phosphate. This is a cathode material. You can see these red balls are there. They are the lithium ion. They are at the channel. They can pass through this channel, and these polyhedras are there. And this is lithium nickel manganese cobalt oxide. This golden ball, yellow balls, they are the lithium ions. They can pass through there. And MO6 polyhedral. This is presently used in our mobiles and laptops. But I don't know. It depends on different company. LG use some composition. Samsung use another composition. And MI brand and basically MI do not make any battery. They purchase from some other company, LG, Samsung, Panasonic, kind of thing. And anode material is graphite, MOS2. I have worked on this material. That's what I have put these examples only. And what I was showing is that in the graphite, you remember that there are some spacing, 0.34 nanometer. Basically, 0.34 nanometer is 3.4 angstrom. So lithium ion can comfortably sit there because lithium ion size is around 0.6, 0.7 angstrom. So that's not at all a problem. So why I choose lithium iron phosphate as a cathode material in my work? Because it has large theoretical capacity. In our mobile, you will see that it is written some 4,000 mAh or 5,000 mAh, something is written. So basically that is the how much coulomb, milliampere hour, ampere and time. Ampere into time is coulomb. So how much charge is stored in that? That's the definition battery cell gives. And I was saying that nickel manganese cobalt oxide is also used as cathode, but their cobalt is used, and cobalt is toxic and costly also. And in our country, cobalt is not that much available. And whereas iron is very cheap, phosphorus is also cheap, but lithium is still a problem. But it is insulator, and lithium diffusion. As I was saying, when it was first synthesized in '97, then at that time its capacity was really low. It was performing of 20 to 25% of its potential. And at that time, basically it was discovered by Professor Goodenough only, and he was not happy. He was saying, "Oh, it is useless material, right? It will not be useful in future." But really, it dominated market for around 10 years. In US, there is one company called A123. They are the master of this LiFePO4 that has gone to the bigger scale. So now these particles, they are bigger particles. So we have to make them smaller. So we have to make it nano. So the lithium ion migration path will be smaller. So the conductivity will be higher. So the diffusion coefficient will improve. And not only that, we have to go, we have to coat with carbon, with graphene. Graphene is also, I have one slide where how graphene is helping that there I have in given it. How do we synthesize it? It's pretty easy. We have to take the lithium source, phosphorus source, iron source, and we have to use and stir and heat. We have to heat it in argon hydrogen. Because the LiFePO4, Fe is a class 2 oxidation. And you know, iron is very sensitive, and it is very sensitive, and it has tendency to go to class 3 oxidation. So somehow we have to keep it in a class 2 oxidation state. So we reduced it, and we have to keep it in inert atmosphere. That's the simple thing we did. And the nano, we made it nano. You can see that we made some these nanoparticles. They are coated with carbon, and you can see the carbon coating is also there. Whereas the bare LiFePO4 right side corner, you can see they are the relatively big chunk, and their performance I'll compare that how nanomaterial has given us the edge. Whenever I am using the nanomaterial, say the blue card, the capacity is around 140 milliampere hour per gram. But whenever it is the black one, it's around 65 or 70. That is the non-nanomaterial, that is the big particle. So making the material in nano and the performance improves in that. That's the point I would like to make. And okay, different charging and discharging we do to test the battery. That okay, you see in the charger, if you look at the charger, it is written that 2 ampere current or 1 ampere current or 1.5 ampere current. So that is really high current. Whether the material can sustain that current. Nowadays, you see the charger, they have this flattened charger. Earlier it used to be pin kind of charger. So lot of current cannot be passed through those kind of pins. It can be passed, but that's not good. That's not good for the health of the battery. So basically we wanted to check that at high current whether the nanomaterial or the macromaterial, the big particles, they can survive. You can see very clearly the nanomaterial they perform, they again can be taken back. But when you see this light yellow color data, only 4 cycles it could run. After 4 cycles it failed. So nanomaterial has importance in battery. And I will talk about the graphene. Graphene is a single layer. Single layer graphene is basically a layer of C6 polyhedra. You see, when it is 0D, if we this one is 0D is the fullerene, 1D is the this is the 1D carbon, this is the carbon nanotube, and 3D this is the graphite. So 0-dimensional, 1-dimensional, 2-dimensional things are there. And whenever it is in the graphene form, 2D form, so it has some interesting properties. Its surface area is very high, 2,600 13. Initially, it was got at that time, but really in lab, it's really difficult to get that high surface area. But people got it. Electronic conductivity of these materials is very high. And in 2010, a Nobel Prize was given to Kim and Novoselov from London, UK, Manchester. Anyway, how this material is helpful? This nanomaterial is helpful in to improve the property, the chemical property or physical property of our battery material that I have shown. These are the SEM and TM pictures. Here I am showing that these are the nanomaterial. And LiFePO4, we coated it with graphene, and it is not basically coated, it is wrapped. And we check the performance, electrochemical performance, and here also very clearly you can see that we could run around 500 cycles, whereas the bare LFP, the red one, you can see only we could run only 15-20 cycles. And here the capacity, I'll show you at C/3 rate. C/3 rate means we are slowly charging, we are gently charging the mobile, and there we got the 160 milliampere hour per gram. Basically, the theoretical maximum value we can attain is 170. So we could really reach till 164 or so, around 94% of its theoretical value. And that I have written here, that 500 cycles we got. So now we'll talk about the supercapacitor a little bit, how this material is used in is useful in these nanomaterials are useful in supercapacitor. Yeah, first of all, let me explain what is the capacitor. Then I'll add this super. Something special is there. That's why super is added. We simply know this capacitor means two parallel plates are there, metal plates, and in between there maybe you can say vacuum also, you can take papers or some dielectric material, and when we charge them, it is like one side gets plus, lots of plus charge, another side gets lots of minus charge, voltage gets generated. Now that's the capacitor, charge capacitor. Whenever we need power from that or the energy from that, we can get from there. And very simple equation that we have seen in our 11, 12 or in college days, that capacitance is equals to epsilon A into D. Forget about this epsilon. A and A by D. A is the surface area, D is the distance. If the surface area increases, definitely C will increase. And surface area will only increase if we use nanometer. And D is the distance, because when we are in nano, 10 to the power minus 9 in that size, so D also decreases. So C increases. And E, this energy density, equals to CV square. So if C increases, definitely we will have higher energy density. So that is the super. Means in normal capacitor, in comparison to normal capacitor, the energy density in supercapacitor is around 1,000 times high. And you see, in case of charged state, all the ions, they are very disciplined and they are sticking on the electrodes. So when we discharge them, we are using short in externally. We are taking the power from by using the external circuit. So the ions, they move to the electrolyte, and in supercapacitor we are using a separator and a liquid electrolyte. We are liquid electrolyte. But in case of normal capacitor, it is totally a solid things affair. Supercapacitor get huge energy in short time. Now in other electronic research, how much time I have? Hello? How much time I have?
Yeah, Dr. Munir, maybe you can continue for another 5 minutes. Is it okay?
Yeah, quickly. Okay, thank you. So in multiferroics, I quickly over this. Multiferroics is when number of more than two or more than two ferroic properties are together. Ferroic means this, we know that ferromagnetic material and we know ferroelectric material. If in a material, if two are together, then we say it is multiferric. Really, generally, it is very, very rare. Mostly in case of ferromagnetic, we need D, unsaturated D, I mean D n, that I mean odd number of electron in d orbital. Whereas in case of in case of ferroelectric, we need d0. So in a material, getting two things is really difficult. Anyway, we made a composite using nanomaterial. That's what I am showing here. That PVDF, it is a polymer. It is a what would I say? It's a ferroelectric polymer, piezoelectric polymer. Basically, what is piezoelectric? When in a material, if we press, if we push some, give some mechanical energy, you have seen that I have seen sorry, I'm showing a photograph where the film is folded. So I'm giving some mechanical stress, some voltage will get generated there. So that's why that's called the piezoelectric material or ferroelectric in this case. When we added iron oxide, that is ferrimagnetic material, and so in a material, both the properties are there. Now the point is whether they are coupling with each other or not. And doing on experiment, we could see this U-shape experiment that yes, just using the magnetic property, we can change the electrical property, or using the electrical field, we can change the magnetic property. So that's what we observed. And one I got this nanomaterials. See how beautiful the nanomaterial has gone. This you see the blue lines, the thin blue lines. They are the carbon nanotubes. You can see these yellow lines. They are connected using nanomaterial, and using their size, they are of some few nanometer only. That's what I was showing. So in short, the size dependent, the structural property, magnetic property, electronic property, optical property, catalytic property, or the sensor, they all depend on, most of them can be redefined. So just after the coming of this nanoscience, we have seen that many physics laws. Earlier, we knew that for any magnetic property, we should have one unfilled d electron, dn. I mean, odd electron is required in d orbital of element. Now we see that aluminum oxide, Al2O3, where no d electron is there, that is also showing weak ferromagnetism. So new chemistry is getting invented, and a lot of nanomaterials which earlier were not so popular, they are coming into the picture, and new vistas of technology. Lot of other, like you have seen that which one I said, the Purite, the water filter was there. The silver nanotechnology is used by Tata company, and nowadays the silver nanoparticles are used in socks. You know, our socks, if we use our socks for longer time, then it gives a foul smell. But if silver nanoparticles are there, they can kill those bacteria, and the stinky nature of the are gone. And nowadays you see the silver washing machine also. I don't know how it works, but there are some nano things I have heard. And in the lighting, nowadays LED light emitting devices, there is a lot nanomaterials are mostly used. So okay, there are some issues also. So whenever I'm talking about nanomaterial, I should not only talk about the rosy beautiful things of nanomaterials. It's just some problems also. Like the nano, what is nano? Typically, people define it that 1000 till 100 nanometer is nano. Below that is nano, and above that is not nano. So, by that definition, 199 nanometer is nano, and 101 nanometer is not nano. So that's not the thing. It is just a vague definition, and it needs continuous improvement. Definitely, for any research, you need continuous improvement. And there are several uncertainties handling in nanoscale and nanoparticle handling. I have seen a lot of people, they do not bother about. They are light, so they are fluffy. They quickly fly and goes inside our body. And this nanotoxicology, when it goes to the cell can engulf these nanoparticles, especially this carbon nanotubes. They can puncture the cells. So those are the some problems of nanomaterial handling. So we have to be very careful when we use nanomaterials. Especially, I'm talking to the students, those who are handling, or those who will be handling nanomaterials. So now I thank you. Thank you for listening me.
Thank you,
Hello.
Dr. Mondal. Hello. Thank you, Dr. Mondal, for your nice presentation. There are a couple of questions from the participant side for you. The first question is, what is the basic criteria of silver and gold nanoparticles so that they are used in medicine?
Yes, definitely. They have to be. We have to check the toxicology and which kind of medicine it has to be used. That is important, and this medical research it has to be done there. And definitely, toxicology is important point there.
Okay. And the second one is why nowadays most of the automobiles are nano coated or ceramic coated, although it requires much more care than any other normal coating.
Please repeat the question.
Okay. Why
in automobile
what? Why nowadays most of the automobiles are nano coated or ceramic coated, although it requires much more care than any other normal coating?
Basically, means why nano coatings are mostly there.
Yeah, I think
that if I simplify the question in that way, it will be this. Yes, it's in case of coating, you have to check the adhesiveness of the particle. That's one. That is the property of the material and the corrosion nature and all. Because in India we have high humidity and other kind of when you drive in city like Mumbai where pollution is very high. This whether they are reacting with each other. So that's the point. I think this is the question participant is making.
Okay, I think so. Okay. Another one is the shapes of nanoparticles get changed on addition of additives. Why?
Yeah, there are which deliberately will do that to let's say if in condition. I'll tell you one example so quickly you can understand. Like let's say I am preparing something gold nanoparticle or silver nanoparticle using sodium borohydride. So that is very harsh reaction. Quickly it will react and maybe within few seconds we'll get the precipitate of silver nanoparticle. So the particles will not get much time to rearrange and quickly it will take mostly the uncontrolled structure and mostly it will be spherical but uncontrolled. However, if we do the reaction relatively slowly, so the atoms will get the time to stack in such a way, in such a fashion, so that the desired structure, wherever it will stick there only where the energy minimization will take place, and we'll get the desired desired morphology.
Okay. The next question is, what is transport number?
Pardon me?
What is transport number? What is transport number?
Transport number I mean, from lithium-ion battery, the question is?
It is also not very clear to me. The only question is, what is transport number?
The transport number is
maybe it is from the lithium. Yeah, it is from the electrochemistry. This in case of lithium-ion battery, the lithium moves from. It is the only cation that is carrying the charge through the electrolyte. I think that, and there it should be one. No other ion should participate. Then it will be complicated. That's what the transport number should be one. And if the student is from BSc, I'm sorry, if the student is from BSc, please, you will see it in in PC of CP. It is clearly written what is
total current carried by particular cation or anion is called transport number with respect.
Yes, and in this case, in case of battery or it should be one. Only lithium ion only should carry that current.
Okay.
Okay, Dr. Mandal, I have some questions. You have mentioned different fields in nanotechnology such as healthcare, potable water, cosmetics, and nanosensors. My questions is now related to nanosensors. First, my question is, what is plasmon peak in fluorescence probe nanoparticle?
Yeah, actually, plasmon peaks is. I'll let me little bit explain it in this way. Gold looks like golden, silver looks like white, and copper looks like copper color. So whenever light interacts with the mobile electron of any metals, so they interact and they give a peak at certain value. And if that peak, let's say in case of gold, the color, the wavelength is in that range only. Now, if we make a lower particle size, the color of gold will not remain golden. It will change to blue, black, like that. And people will be very unhappy because gold is lost in color.
Okay. My another question, Sam. You have mentioned the different types of reducing agents such as malic acid, ascorbic acid, aldehyde. Why did not you mention the natural products such as glucose or cane sugar juice? Why did not you use?
Excellent. This is really excellent question, and I love this. When I joined, I started thinking this nanomaterial and all, and I used to see that people make these kind of things. And truly speaking, I did not knew that in our BSc days we did that experiment, this silver test or this copper oxide, that there was some Thelling's tolerance reagent. And then I found, yes, glucose can be used. We used glucose, or you can use other extractant. Wherever aldehyde group is there, that will be able to reduce the silver cations. And another positive thing is that this organic part that can coat the silver also, and it will protect it to agglomerate. So the stability will also be high.
Okay. My another question is that from my own experience or my own research in sol gel method, different times we have seen that the nanoparticles are now agglomerate. What are the way to minimize these agglomeration?
It's okay. Kids are like that only. My kids are also doing like that in lockdown. They should be entertained. I think we should put them here also. Anyway, the question is the agglomeration problem. So basically, yes, that is a problem. That you already, whatever we are talking, that glucose or other kind of like some we extracted some fungus. From that fungus extract, there are some protein. Cysteine was there, and we observed that cysteine could itself coat the particle, and the particle could disperse. So agglomeration was less. This is really a surface functionalization. We have to intelligently functionalize the surface. Now, the surface. Let me finish it. The surface are mostly the zeta potential either positive or negative, or we have to make it positive or negative. And the opposite of that, we have to coat with that. Then the surface will be protected. Yeah, please.
My another question is, when you are carrying some or doing some nanoparticles such as graphene layer or etc. Do you try or put the DFT calculation or showing by DFT calculation by band gap theory or others?
We don't do in our group, but in DRC also there are a lot of theoreticians. They do that. Yes, my friends are there. They do that.
Okay, thank you.
Okay, Dr. Mondal, Professor Chirantan Hajra from our college has some questions for you. I would like to request Chirantan to ask him the question.
Yeah. Yes. Actually, in case of electrolyte, that worldwide we have standardized around 20% doping of yttria is required for YSZ, And for LS, the cathode side, I really forgot the value. Cathode and anode, I really forgot the values. But yes, I can tell you what was what we used. But the basic aim is to make it electronic conductor and ionic conductor. Yes. Yes. Yes, very nice question, and this is the problem every day we face, and we try to answer these questions. Like first, once we make the material, and if we take the X-ray diffraction, if the material is doped at the lattice side, then the lattice will decrease or increase as per the depending on the size of the dopant, right? If I dope something bigger, it will be big. If I dope smaller, then it will be small. That's one point. Okay, and but yes, if the doping is really low, like less than 1%, then really we break our head. Really, we also get then XPS and other exotic techniques we have to use. No, in EDAX it sometimes gives average picture. But in EDAX we can see if, whatever you are doubting that if let's say it is precipitating on the surface, EDAX in the BSE mode sometimes we can detect them, but not always. Thank you very much. Thank you for giving me this opportunity. I really love to talk with you.
Okay, thank you, Dr. Mondal. I don't see any further question right now. In that case, let me thank you once again for your valuable time and for your wonderful presentation.
I'm sorry. Now I see the time is 1:47. Maybe many of
no problem. So we are now at the very end of the today's webinar. Right now, I would like to request Dr. Sadhan Pramanik, Head of the Department of Chemistry, Hooghly Women's College, to conduct the last part of this webinar, the valedictory. Dr. Pramanik, please start your valedictory session.
Okay, thank you, Anup. First of all, I would like to thank all the participants to participate their kind attention for the last 2 days. This is our great pleasure to have a more than 200 participants participated in this webinar. I convey my deep gratitude to honorable speakers, Dr. Madhusudan Maji, Dr. Suman Desarkar, Dr. Kanak Rai, and Dr. Balaji Prasad Mandal to present their knowledge and research updates with us, and hope it will be helpful to the participants as well as our students. In these 4 lectures, we have listened different topics of chemical sciences, metal and heterogeneous catalysis, electrochemistry regarding nanotechnology, etc. And the sessions were really nice and enjoyable. I would like to thank our principal, Dr. Shima Banerjee, and IQAC coordinator, Dr. Samolina Goswami, for their kind advices and constant encouragement to organize the webinar. My thanks to coordinator, Professor Chirantan Hajra, for his advices and technical assistance, and my special thanks to my colleagues, Professor Satyajit Biswas, Dr. Biplab Mandal, and Dr. Onu Biswas, and also Dr. Horidev Seal of our departmental teachers. We are ending 2 days national level webinar. Now, I am requesting all the participants to fill up feedback form. Link is available in the WhatsApp group. Thank to all of you. Thank you.